So what is object-oriented programming? Well, it was invented in the 1960s for a language called Simulus 67, and then it was later picked up and used a little more widely in a language called Smalltalk. The simplest way to talk about object-oriented programming is as a paradigm or as a way of organizing our code. As you've probably realized, all programs are comprised of code that's designed to process data. We store the data temporarily in variables, and then we call functions to process the variables. The object-oriented paradigm organizes the data into specially designed entities called objects, and the functionality for processing the data into specialized functions that we call methods. The design of these objects and methods is specified in a kind of a blueprint, which we call a class. This paradigm is one of the most important advances in software design. It promotes collaboration and the extension and maintenance of our code. And because its ability to help us manage complexity is so profound, it is the primary paradigm used for software design. It's hard to overstate just how important it is to programmers every day. And it's simple enough to begin implementing that it can make your coding work easier every day, too. Now, as a way of explaining the difference between object-oriented code and non-object-oriented code, let's look at a really simple example. The code on the left is what we call procedural code, and that's the word they use when they mean non-object-oriented. As you can see, we're taking an integer and passing it to a function called increment, and then catching the result in the same variable name. And in the end, we print the integer, and you can see it's been incremented twice. Compare this code to the code on the right. This is not an integer in the object paradigm. This is a myCustomInt object. It's an object that I designed myself in a class called myCustomInt. The myCustomInt design includes a method called increment, and I'm calling increment on the object. Now the result is the same, and you can imagine that within the myCustomInt object, there's an integer there. But again, it's not an integer. It's been designed specifically to my specification, and I've included a special method to work with it. It doesn't illustrate exactly why we need objects, but it does show the difference. In the procedural paradigm, we might design a function that works with an integer, and it would be doing the same work as the object. The difference is, in the object paradigm, we actually have a custom type of object that has its own special method for doing this incrementing. The functionality and the data are connected, and that's really the best way to begin thinking about objects. Data plus functionality. Now, just to satisfy your curiosity, here's the code behind both of those examples in the previous slide. The code on the left should be self-explanatory, but I won't go into what's going on the right here because that's going to be the topic of some upcoming lessons. Now, it's going to take several lessons, really, for it to become clear to you exactly why we need object-oriented programming. The short answer is that it just makes our lives easier. And when we have very complex programs, objects make it so much easier to handle the complexity, also to work with other developers on the same code, and to communicate exactly what the library does to people who might use it. For this reason, object-oriented programming is a universal paradigm used in many languages. And it's safe to say that learning object-oriented programming is a necessary next step into the larger world of software engineering. Now, a full description of objects wouldn't be complete without talking about the three pillars. We're going to discuss each of these in upcoming lessons. For now, I'll just let you know what they are. I also might mention that I had this as a question in an interview many years ago. What are the three pillars of object-oriented programming? I wouldn't be surprised if they're still using this question. The answer is encapsulation, inheritance, and polymorphism. Those may not mean very much right now, but we'll be discussing them much more extensively going forward. This lesson is about how Python is object-oriented. And understanding that can give us additional insight into the language as well as into objects themselves. So you may have heard that everything in Python is an object. But what does that mean? Well, most other languages make use of entities called primitives. These are variables that are not objects. But in Python, everything is an object, including primitives. So then what is an object? You can find varying definitions on the web, but here's my definition, and it'll obtain for the purposes of this course. An object is an entity that holds data in the form of attributes, is of a particular class or type, and is associated with functionality in the form of methods. Primitives like integers are objects in Python. The type function returns the type of any Python's objects. You can check by simply printing the type of, in this case, myint, or the type of meister, and we'll compare the two. I'm running this in the PyCharm IDE. You may notice I'm typing clear here before I go ahead and invoke Python and then the name of the script that I'm running. Clear is just clearing the screen. And then also, after all of my scripts, I'm typing print twice. That's because I just need a little extra space before we see the command prompt again. That's just to make things clear. So you can see that the type of that integer 5 is type int, and of the string is type str. Int and str, as you probably know, are the names that Python uses for integer and string, respectively. So it's clear that even integers have a particular type. Keep in mind that type is roughly synonymous with class. This means that we can say that myint is of a type int, and we can also say it is of class int or class integer. And the same thing would be true of string. It is of type str or string, and it is from the string class. And by the way, the shorthand int and str are synonymous for integer and string. They're just Python's internal names for the integer and string class, and I'll often use them interchangeably. So now I've gone ahead and written out a few more objects. You can see we have a list, a Boolean value, and the none value, which is Python's null value. And we also have a function here called myfunc. And I'm looking at the type for each one of them. I've simply taken each object and placed it into the type function. And let's run it and see what we get. So indeed, every single object in Python has a type, including the none value, which, as I said, is Python's null value. It's of type none type. The function, too, is a variable that has a type. So even Python's functions are of type function. They're also objects. And then look what I did at the bottom. I took the type of the list, and I assigned it to a variable, and then I checked the type of that object. And in fact, the type of an object has a type. It's of type type. Now that looks a little bit redundant, but it does illustrate how important it is to the Python's designers that Python be consistent. When we say that everything is an object in Python, we really mean it. It means that every entity in Python is an object of a particular type, and as we'll see in a second, every object has attributes as well. So now I'm going to use Python's interactive prompt. I'm going to get there by typing out the full path of Python. You can usually just get there by typing Python at your operating system's terminal window. I'm in the Mac operating system here, and I'm using the terminal program. But if you're on Windows, you can get the same result by going to your command prompt. And that's usually obtained by going to the Start button, clicking on Run, and then typing in CMD in the Run box. I'm going to find out what the attributes are associated with this integer. Again, in other languages, an integer would be a primitive, but in Python, it's an object. Here we see the integer's attributes. Don't be put off by the number of attributes here. There's quite a few, and you're never expected to know what any of them are until you need one. Anything you may need can be easily looked up. The names here that begin with double underscore are what we call private or magic attributes. They're attributes that are usually used internally by Python itself. Other attributes of an integer, like numerator or real, are attributes that return a value that is the numerator of the integer or the real value of the integer. In this case, it's the same number. Other attributes of an integer might be a method, like the bit length, which returns the number of bits necessary to render this integer in binary. As I say, many of these attributes are somewhat obscure. We just want to take what we need and leave the rest. So in this lesson, we looked at how Python is object-oriented by default and how all entities in Python follow the same rules of objects. The reason for this has to do with Python's elegance. As you continue to explore the language, you'll see again and again how important it is to the designers of the language that it be consistent. This is what we mean by elegant. It simply means that anything that you learn in Python, any particular rule, is usually applicable across the language. In other words, the designers were trying to avoid special use cases. Other languages may have special rules that aren't known to everybody. And so in order to be an effective programmer, you often have to be a power user, which means you know a lot of special rules and tricks. In Python, they try to avoid that. And the design decision to make everything an object means that there's a consistency that we can rely on. The overall impression that you may get is that everything makes sense in Python, and that'll become clearer as we move forward. Here's a quick note about modules versus classes, because I've found among my classroom students that there's sometimes some confusion. Basically, a Python module is simply a file that contains code. This code can be executed directly, or it can be imported. When we use the word module, we often mean code that's intended to be imported, although the generic definition of module is simply a file that contains Python code. When we import a module, the code becomes available to us through the module's name. Here's a module that we're calling mymod. It's not designed to be executed. It's designed to be imported. You can see that we have an integer here, var, and a function called doThis. Now we have another file called test.py where we're importing mymod. As you know, importing a module means you leave off the .py extension. If you say import mymod, Python will import mymod.py. And now, let's execute it. We see 10 and then executing the doThis function. And of course, that's exactly what we have in mymod. We're accessing var and doThis through the mymod name. This is the standard way to import a module. The mymod namespace holds the mymod variables, var and doThis. And there are other ways to import as well. We can rename mymod as mm. We simply reassigned the name mymod to the name mm, and now we can access the variables through that name. The third way to do it is to import variables directly, and then that's when we use the from keyword. From mymod, import var and doThis. Now we can use the variables directly. This is just a little primer in how to use modules. Whichever method you choose doesn't really matter. The only reason you might choose one method over another is for convenience and clarity. Finally, let's discuss modules in reference to classes. Sometimes these are confused, either because of the notation that we're using, or sometimes it's because a module may just contain one class and they sometimes seem synonymous. Remember, a module is simply a file that contains Python code. A class definition, which we're going to look into shortly, is simply Python code. In this somewhat confusing example, the designers of the decimal class decided to name the module decimal and the class that's inside the module as decimal. So that's why we're able to say, from decimal, import decimal. In this example, case really matters. So the lowercase d decimal is the module, and the uppercase d decimal is the class that's inside the decimal module. We're going to see that all classes begin with an uppercase letter. That's a standard Python convention. As we mentioned, you can import specific variables from a module using this form, from decimal, import decimal. We're saying from the decimal module, import the decimal class. And now we're using the decimal class the way it's intended to be used. You pass a string that specifies which value you'd like to use, and it creates a decimal object. Let's run it for you right here. So here we've created two new decimal objects and we're adding them together. The details aren't really important. The illustration here is just to show you that a module is just a file that contains Python code, and a class is simply Python code. That's the difference between those two. Let's talk about what you'll need to take this course. This course assumes a basic familiarity with Python. It's important that you not only be able to write programs, but that you be able to debug them. Of course, this is a necessary skill in any language. This simply means that you've written some programs and worked out the issues when you got errors. And as we all know, you can't really learn something until you've made a few mistakes. I've listed out here on this slide a few of the things that you should know already if you've met this requirement. If you're a beginner, or you need to brush up on your Python, or you'd just like to learn from square one, Courses on introductory Python are available from this publisher. To do the exercises and try out the examples in this course, you only need Python and an IDE or text editor. We'll talk about the IDE shortly. The examples in this course are written for Python 2, which means Python 2.5, 2.6, or 2.7. The current development version of Python, around 3.3 as of this recording. So you might wonder why we're not teaching using the latest. The answer is Python 2 is still the dominant version among developers worldwide. And the main reason for that is that Python 3 is not backward compatible. If you can imagine having a large library of Python 2 code, switching to 3 is not a trivial matter. I think the statistic as of the time of this recording is that approximately 80% of Python developers are still writing code in Python 2. You'll definitely want to become familiar with it. You may find that for the examples in this course, the differences between Python 2 and Python 3 are minor. In the Documents section, I've added a short summary of the most common differences between the two versions, and how you can convert any of the exercises to Python 3 if you're using that version. In addition to any standard distribution of Python, and if you're on a Mac, Linux, or Unix operating system, this is automatically installed. You'll need the YAML module to complete the work in the data serialization section near the end of this course, and we'll also be discussing PyTest, which is a module that must be separately installed. I've also included some information on how to install modules in the supplementary documents. Finally, we'll want to choose an IDE. In this lesson, we're going to talk about choosing an IDE or a text editor for writing and running your programs. Now, you may have already chosen your IDE or text editor and established your workflow when writing and running Python programs. If not, let's talk about what sort of tool you'll use to do the exercises in this course. The more coders you get to know, the more tools you'll learn about. Every software developer has his or her own favorite set of tools. Writing code, however, boils down to choosing a text editor or an IDE. IDE stands for Integrated Development Environment, and it's really just a fancy word for a program that helps you write programs. An IDE is really just a text editor, but it's been integrated with a set of tools that makes it easy to write and run your programs. Your code is highlighted in a way that reflects the parts involved, and you may find that your functions are indexed so that you can easily jump from one function to another. Probably the most useful feature of an IDE is its debugger. This usually means a visual environment in which your program is being run, with a cursor appearing on each line of code as it's being executed. You'll have the opportunity to stop the code at any point, check the value of variables, and even manipulate the value of variables before resuming execution. It can be an extremely useful tool to have. In this page from Stack Overflow, a helpful contributor has listed out many of the features that we look for in IDEs, and then a list of IDEs that support each feature. Some of the more popular IDEs for Python are PyCharm, Komodo, and Eclipse, which is actually written specifically for Java but has a Python plugin. Most of the features on each IDE are pretty much the same. Really depends on what you're comfortable with and what you like. As far as a visual IDE goes, I prefer PyCharm. I like the way it looks and feels. I like the organization of its feature set. It gives you the feeling that the developers were very careful about coming up with the most convenient features. You can make changes to your code and run the code without having to save the file. Other IDEs like Komodo, for example, which I just sampled, requires that you hit save every time. You also have the choice of a text editor if you'd prefer over an IDE. Personally, at work, I use VI. That's a simple text editor for Unix, but it has a lot of built-in features and it's possible to configure to your own taste. If you do want to keep it simple, there's a number of text editors that are available. On the Mac, Text Wrangler is a very good one, and on Windows, Notepad++. Both of these are IDE-like. That is, they do things like syntax highlighting, and they'll even execute your scripts for you. If you want to go even more bare bones, you can go with Notepad for Windows or TextEdit for Mac. Whichever IDE or text editor you choose, you can always choose another one later on. In this lesson, we're going to redefine some essential object-oriented terms and programming concepts. If you're eager to get to some code, feel free to skip ahead. And if any terms are confusing, you can always return to this video for the conceptual overview. All of these terms are defined in the glossary in the working files, as well as here. And you should keep the glossary handy to look up any terms you might have forgotten. It may be a little disorienting having all these new terms floating around, but we can't talk about classes without these terms. They're central to the paradigm. You'll also find out that these terms are in common use anytime anyone is discussing objects and classes online. As we mentioned, a class is a kind of factory for an instance. This factory contains a blueprint which describes how to make instances. Instances, or objects as they're also called, are constructed from the class. In most cases, multiple instances can be constructed. Again, the class is the factory and the blueprint, and the instance is a kind of a widget coming out of the factory. So the structure of each instance will be identical to every other instance. As we saw in an earlier lesson, every instance has a set of attributes. These attributes are defined in the class. So every instance of a particular class is expected to have the same attributes. In the code example here at the bottom, we have a string which we're labeling var. As you may know, any string will have access to the upper method. Thus, any string that is created is part of the string class and therefore has an upper method. The string class defines upper, and thus all strings constructed will also have access to that callable attribute. Remember, I'm calling a method a callable attribute. So every method is an attribute, but not every attribute is a method. Type is just a term meaning the type of object, which really means which class the object comes from. We may say that an instance is of type string, or we may say that it came from the string class. Remember, we defined an object as a unit of data of a particular type associated with functionality. We'll get to the data in a little bit, but let's review the term method. A method is really a function defined in the class that can be used by the instance. So look at the example below. What type of object is var? It's a string. So we can say that it is of the string class and that it is of type string. We can also call it a string object or a string instance. And on the last line, we can say that we're calling upper method on the string object or instance. Let's talk about these terms and about classes and creating instances a little more conceptually. Here's a real-world metaphor for our class and its instances. Again, we're indicating the metaphor of the factory blueprint that produces instances. In this case, we might consider a car factory that produces cars. All the cars are mostly identical in that they do the same thing. In our limited example here, we can say that cars can start, stop, and honk the horn. All the instances can do this. This is from the blueprint, and all of it is defined in the class. So now let's introduce a new concept, the idea that each instance has its own data. Again, remember the definition of an object, a unit of data with associated functionality. Now we're seeing it fully realized in this metaphor. Each car can stop, start, and honk. In code, these would be rendered as methods. But once they come out of the factory, each car has other attributes which are specific to that car. The car's speed, for example, or whether its doors are open and closed. Once the instance is constructed, it can set its own values to its attributes. What you should notice is that the type of values that are being held is the same between each of the instances. In other words, they all have a speed attribute, they all have a left door attribute, they all have a right door attribute. But the state of those values is different for each car, because each car is being used differently. So there's a difference between the blueprint, which is defined in the class or the factory, and the state of each instance, which is defined by its use. Let's look at what the code might look like if it was the story of a car factory producing 2 cars. What you see there in capital C car, that's the class. We happen to be passing a color value to the constructor. We'll get into that a little bit later. But if we want to produce a red car, we pass red to the car constructor and we get back a new object. You may remember from one of our earliest examples that this constructor produces a new object, and this is an object of type car. We have red car and blue car. We could have called these X and Y. It doesn't really matter what we called the variables. What matters is that what came out of the car constructor is a car object. So now, whether it's red car or blue car, we can call start, stop, open left, etc. on each of these instances. The state of each car will change depending on what we call. So the red car may have an open left door and a closed right door, etc. Blue car may have started, red car may stop. This is what we call the state. And we're going to see that it's possible to set additional attributes in each object that indicates its state. Here's another theoretical example that I sometimes use in my in-person class to illustrate what classes and objects mean. Consider an ATM machine. Before you slide your card into the machine's a little bit like a class. In other words, it knows how to do a bunch of things, but it's not able to do any of those things because it hasn't been turned into an instance. Once you do slide in your card, however, it's more like an instance. In other words, it has a piece of data to hold on to. Remember the definition again: a unit of data with associated functionality. Now the ATM is prepared to do all the things it was designed to do. Before you put your card in, it was just the idea of an ATM. Now that it knows who you are, it's your machine. It can refer to you by name. When you press the withdraw button, it'll be withdrawing from your account. When you press the check balance button, it'll be checking your balance. So in this lesson, we introduced and defined a set of terms and also introduced the concept of instances having their own data or state, as well as access to common functionality defined in the class. If anything's confusing about instances and classes at this point, think about the metaphors that we've been using. You can also keep this video handy to refer back to as we look through examples, but it should all come clear. This is the first in a series of lessons in which we'll break down the mechanics and behavior of classes and instances. As we discussed, classes are instance factories, and they define a blueprint for creating an instance. Let's create our first class, and then we'll go right ahead and create an instance of that class. I'm going to create a class called myClass, and I'm not going to do anything with it. I'm going to make it the simplest possible class, that is, a class that doesn't do anything at all. For now, let's postpone discussing the word object in this example, because it has to do with class inheritance, and we'll be discussing that soon. Pass is unique to Python. It indicates that a block has no contents. It's, of course, unique to Python because of the way Python handles its block structure, by reading indents. If we didn't have anything in this block, Python would be confused that there's seemingly no end to the block. The inclusion of pass indented means this is some block. When we get back to the left margin, we know we've reached the end of the block. So what we have here is an empty class definition. Let's create an instance. So what is this object? From previous examples, you can infer that this object is a myClass instance or a myClass object. Let's print it and see what it has to say about itself. Looks like we have a myClass instance, all right. The main in front of the myClass refers to the namespace. It's the namespace of the script currently being executed. This is a module thing, so we don't need to worry about it for our purposes. The main point is that by printing the instance, we're able to see that we indeed have an instance of myClass. The hex code to the right refers to the address in memory where the object is being stored. This is also something that we don't need for this lesson. It simply indicates the identity of the object by showing you where it's being stored. If you create a second instance, you'll see that it has a different address. So let's do that right now. That obj equals myClass. Actually, I'm going to do something I did before, which is include a few print statements so that we get a little more clarity. So there it is. We have two myClass instances, and you'll notice that the hex code is slightly different. It points to a different address in memory. We use this hex code only when we're interested in making sure that two objects are the same or different. Because as you know, the labels that we assign to each object are arbitrary. I get to choose whatever label I want to assign to each object. There's no way of identifying the object except by actually printing it and looking at the hex code. Now let's take one more step and create a variable in the class, and then show that the instances have access to that variable. What we've done is added a variable to myClass. We've called it var. And then look what we're doing here. We're taking each object and saying object.var, the same name that we used in the variable. Let's see what we get there. Sure enough, we see the value from the myClass definition in each of the objects. How are these variables available to each of the instances? Well, this is part of the magic. However, we do know that an instance knows from which class it came. So when we ask for an attribute from an instance, the instance looks for that attribute in the class. We're going to see that it looks for the attribute in its own set of attributes first, but for now, we can see at least that it's able to find the attribute in the class. This starts to paint the picture of how classes and instances interact, but it'll take a few more lessons to complete it. For now, let's delineate the first 2 of 6 points that you'll want to absorb in order to understand how classes work. An instance of a class knows what class it's from. Variables defined in the class are available to the instance. This is the first 2 of 6 points that are going to build our understanding of the mechanics of classes and instances. So in this lesson, we've shown that classes are automatically able to create instances. We've demonstrated that each instance is aware of the class from which it came. And lastly, we've shown that variables defined in the class are available in the instances through object-attribute syntax. Again, we're saying object.attribute. And the attribute is actually not located in the instance. It's located in the class, but we're able to access it nonetheless. And that's because of the relationship between the instance and the class. In the next lesson, we'll see how variables defined in the class can also be functions, and that's how we get to methods. In this lesson, we'll look at methods, how they're defined, and how they work with instances. The first step to that understanding is what we just covered, that variables defined in the class are available to the instance through attribute lookup. Here we have a string being defined in the class Joe. We call the string greeting, and we're able to print the greeting through the instance. So the string is accessible through the instance because when we access an attribute through the instance looks for that attribute in the class variables. Any variable defined in the class is available to the instance. Because the instance knows it's a member of the class, it knows to look in the class for attributes when we ask for them. So let's run this and see what we get. I see none at the end. I don't know if you're familiar with that sort of error. I mistakenly called print on the method, and that's not what I intended to do. So that's why I got none, because when a function doesn't return anything, and this is true of a method as well, it actually does return the none value. So you can see that I am printing that statement, which means that we successfully called the callMe function. Now there's an additional feature to keep in mind here, and this is what we might call a magic feature, since it's not immediately apparent by looking at what's going on. Look carefully at the word self in this method definition. There's an argument required when calling the callMe method, and this argument is going to be assigned to the label self. But look at the callMe method. Do you see an argument? As you may know, under normal circumstances, Python requires that if the function or method definition has an argument, then when you call it, an argument must be present. And if the arguments being passed in the call are not the same as the arguments defined in the definition, there's an error. And yet we don't have an error. There's apparently no argument being passed in this call. And yet the definition itself requires an argument. That's a single argument requirement. What if we just take that out? Let's turn it into a method definition that doesn't require an argument, and let's run it again. Wait a second. CallMe takes no arguments, but one was given. It's telling us that this call actually passed an argument, and yet I don't see one. So it's pretty clear that this Joe.callMe is passing an argument, and yet there's nothing in the parenthesis. The answer is that there's a little more magic going on here. And here's the rule. When we call a method on an instance, the instance gets passed as the first argument automatically. This is a default implicit behavior that we should be aware of. Again, when we call a method on an instance, as we're doing right here, the instance is passed as the first argument to the method. So we'll put self back in here. Run it again. Now everything seems to be good. And let's go ahead and ask ourselves then, what is self? Well, as I mentioned, when a method is called on an instance, the instance is passed as the implicit first argument. So let's print self and see what we get. Do you see what we have here? It's the ID that an instance gives when we try to print it. And you can see again, we say main, which I mentioned before is the namespace that we happen to be in, not something we need to worry about at the moment. Joe, which is the class, so this is a Joe instance, and a hex code. The hex code being the address in memory where this object is being stored. And actually, we can prove that this is the same instance as the one that we called it on by printing this Joe down here in the main body of the program. Now look at the two hex codes. They're identical. Now we've actually used the hex code to identify that these two objects, or really just the one object, is being printed in two different places. So again, we're printing self here, and we're also printing this Joe. This proves conclusively that callMe as a method is passing the instance directly, and we can see that from the output. So in this lesson, we learned that instance methods are variables defined in the class and accessed through the instance. We also demonstrated that when we call an instance method, Python passes the instance as the first argument. Because of this automatic passing, instance methods are known as bound methods, and sometimes you'll see this term mentioned in error messages. The binding is between the method and the instance. When we call the method on the instance is passed automatically. So there's an automatic connection. This adds another point to our 6 points to understanding classes. A method on an instance passes the instance as the first argument to the method, and this instance should be named self in the method. So going back one more time, this definition where we have self as part of the arguments list, this is standard when we talk about instance methods. Since we know the instance is going to be passed first, we always notate it in the definition, and we always call this instance self. That's a convention that you're really going to need to follow, even though you could potentially call it something like X. You shouldn't. The instance is always called self when we're talking about it in the method itself. Next, we're going to see how instance methods can be used to modify the data stored in the instance. We're about halfway to understanding the mechanics of classes and instances. And up to now, we've seen how we can use object.attribute syntax to access variables in the class. In this lesson, we're going to see how objects themselves can have their own attributes. Once again, looking at the definition of an object, we now know that instances can access methods in the class, of course, the instances of a particular class or type. And now we're going to look at the unit of data we've been talking about, the attributes that can be associated with an instance or an object. And remember, I'm using those terms interchangeably. Here's an example from before. This is about the time in my in-person class that I asked my students a little quiz question. What is self? If you're not sure, stop the video and think about it for a minute. I'll tell you right now that you must know what self is. If you don't, you'll want to get clear on it right away. In this case, on the second line here, self is the object on which the method was called. So you can see at the bottom, we're calling the doThis method on myInst, which, as you can see, is an instance of my class. So the correct answer is self is myInst. It's the instance of my class. Or more generally, we can say, in every case, self is the instance upon which the method was called. So now let's get to the meat of this. Let's have the doThis method actually do something. Let's have it set a value in the instance. I'm going to make use of the random module, which can generate random numbers for us. And instead of just printing something here, I'm going to generate a random number. Random has a function called randint that will generate a number according to my specs, and I'm asking basically for an integer between 1 and 10. We call doThis as before, and then let's just print the instance attribute that we set earlier. We'll run this 1, 5, 10. Notice that every time we run it, we're generating a new random number. This is happening when we call the doThis method. So this is something brand new. Look at the last line, print myInst randval. This is the same syntax we've been using to access class variables, but there is no class variable with this name. Now look at this line above, self.randval equals. This is where we're setting the value of the attribute randval, and we're setting it not in the class, but in the instance itself. This is the data that we were talking about when we said that an object is a unit of data. It's the data we were talking about in the metaphor when we said that a car might have a state, like its left door is open. It's the data we were talking about when we said that an ATM has your account number. Instance values are stored right in the instance, using the instance's attributes. And setting the instance's attributes is as easy as saying instance.attribute equals value, as we're doing here. Again, we call the attributes of an instance the state of the instance. In other words, what's going on with the instance? What's going on with the object? What values have been set in the object? And of course, those values are set through the attributes. So now we're getting pretty close to completing our understanding of how classes and instances work. In this lesson, we saw how an instance can have its own attributes, and that the attributes make up an instance's state. In this lesson, we'll look at encapsulation, which is one of the three major facets or pillars of object-oriented programming. Remember, early on, I introduced the three pillars. This is the first one, encapsulation. In my class, we've defined two methods now, setVal and getVal. Take a look at how we're calling setVal in the code below the class, here. One argument, an integer. Now let's look at the definition of setVal. Two arguments. Why is this? Because as you know, any instance method, that is, a method designed to work on the instance, implicitly and invisibly, passes the instance as the first argument to the method. So in getVal, we have no arguments in the call parentheses. And in the definition, we have one argument. Again, that's because the instance is being passed as the implicit first argument. So what is setVal doing? Okay, it's taking the argument and it's setting it as an attribute in the instance, under an attribute called value. And keep in mind, all of these names, getVal, setVal, A, B, the value attribute, the myClass class, all of these names we can determine at will. They follow the same naming conventions as for variables. So setVal is what we call a setter method, because it sets a value in the instance. So can you guess what they call getVal? It's a getter method. You'll often hear these terms used in discussion groups, on Stack Overflow and elsewhere, and they simply refer to methods that set or get values from the instance. Now, occasionally a student will ask me whether an attribute can't be set in the instance down in the main body of the code. In other words, if A is self and B is self, and we're setting the attributes here through self, could we just set them down here? Let's try it. Yeah, absolutely. You can see that we set B to 100, and we originally set A to 10, but then after that, we set A to hello directly. In other words, we access the attribute and set it right here in the object, the same way we do up here in self. In other words, there's no restriction against doing this down in the main body of the code. So then the next question might be, if I can do it here in the main body of the code, why write a whole method to do it? The reason is that using such methods provides a kind of a gateway for any operations having to do with the instance's state. And in this gateway, we can ensure the integrity of the instance's attributes. By using these methods, we're encapsulating the instance and ensuring the integrity of its data. Take a look at this example for a class called myInteger. The point of this class is to produce instances that will hold integer values with a method to increment the value. The getVal method is the same, but take a look at the setVal method. What's going on there? Well, we're attempting to convert whatever is passed to the method to an integer. That's what's going on right here. We're going to discuss exceptions in detail a little later, although hopefully you know a little something about that already. If not, what's happening here is that if the value passed to int in this line is not a value that can be converted to an integer, a value error exception will result. The except block here is catching the exception. As you can see, if the user passes a bad value and a value error exception is raised, the method will simply return without setting the value. Again, if you're not clear on how exceptions work, all you need to know is that if a bad value comes in, that is one that can't be converted to an integer, and Python doesn't like it, we simply return from the method without setting any value. However, if the error doesn't occur, we do get to this line. So this line is only going to be reached if the value can be successfully converted to an integer. In other words, if it is an integer, or maybe if it's a string that has an integer in it. So the overall effect is that setVal won't let us set anything but an integer in the val attribute. And this is key because later on we're incrementing the value. What if we decide to get smart and we change the value of the attribute directly? Instead of setting it through setVal, let's just say I.val equals hi. And you'll remember this is what we did before. The question was, can we set attributes directly in the instance down here in the main body of the code? And the answer is yes. Let's try it and see what happens. Now, in order to see what sort of problem it might occur, we're going to call increment value. Now, this would normally work in the case of an integer, because as you can see, increment val is simply taking the current value set in the attribute and then adding 1 to it, assigning it back to the attribute. Let's try it and see what happens. We got an error. Cannot concatenate stir and int objects. Why did that happen? It's because we set hi in val. Now, if we had done this through setVal, the method wouldn't have let us do it. This is the gateway I was talking about. It's the gateway that ensures that our value in val is always going to be an integer. By requiring the use of setVal, we're able to ensure the integrity of the data in the object, and this is what we mean by encapsulation. So setting the value in the object without the use of the setter method, this is called breaking encapsulation, and it's a big no-no. Later, we'll see ways to enforce encapsulation and take control of attribute setting, even when it's done directly in the object, so that we can, again, ensure the integrity of any data going in and reject any that isn't working. We've seen how setter and getter methods can implement encapsulation, the first of the 3 pillars of object-oriented programming that we'll look at in this course. In this lesson, we'll learn about the init constructor, which is a special method that allows us to initialize attributes at the time that an instance is constructed. As we've seen, attributes are traditionally set using a setter method. But what if we want some attributes to be set right at the beginning, before an instance is even created? This can be done in the constructor. We've added a new method, which is called init, which, by the way, is a common shorthand in computer science for initialization. The double underscores before and after the name signify a private or magic method. It's called private because it's intended to be used internally, not called by the user of the class. And it's called magic because it's usually called automatically when a particular event happens. In this case, init is called automatically anytime a new instance is constructed. Like other instance methods, init has a self in its arguments list. This is actually the first appearance of the instance. It hasn't exactly been passed from anywhere, but because it's an instance method, it is present. And it's present, of course, because we're going to modify it in the initialization. We'll be setting its attributes. And by initializing an object, we simply mean setting attributes, or possibly doing other preparatory work that's necessary when creating a new instance. This particular init method is setting an integer value in the instance, here. We also got a print statement that is declaring that init is being called. This is just for demonstration purposes. This particular class is designed to create instances whose integer value can be incremented, which is what we're doing here. And you may notice that PyCharm is suggesting that we replace this statement with augmented assignment, which means plus equals 1. And we could do that, but I'd like to make this especially clear. So in this code, we're calling increment twice, which means that the value of the val attribute is being incremented twice. And so at the end, when we print the val attribute, we see 2, which makes perfect sense. We can also pass a value to init if we put that in the initialization signature. And then we can use the constructor to take the argument and set it in the object. In other words, if you look at the call here, we're creating a mynum instance by passing an integer. And up in the init method, we're accepting that integer here in the value attribute. Don't forget that every instance method has self as the first implicit argument. And any additional arguments that we pass will be assigned to the additional variables in the signature, the arguments list that's in the method definition. In this case, we're not actually calling a method directly. We're just constructing a new instance. But because init is called automatically, we have the opportunity to pass arguments to that method. Just running it. Okay, great. So we see calling init and then 7. The val attribute started at 5. We called increment twice, and of course increment took val and added 1 to it each time. So that's why we see 7 at the end. Change my little comment to fit. But what if we pass a bad argument to the constructor? We get an error. Again, this is the same error we saw in an earlier lesson. We've set the attribute to a string, and then when we called increment, Python tried to add 1 to the string. And as I'm sure you know, we can't add or concatenate a string to an integer. We get a type error. And Python tells what's wrong. Cannot concatenate stir and int objects. It was attempting to add 1 to hello. And this is just like the problem that we had earlier when we were demonstrating a setter method with a gate. And we clearly need one here too. We should do something similar in our constructor. We've modified the code considerably here. In particular, we've added the integrity gate that we talked about before. By integrity, I just mean that if it isn't an integer, which is what we really need the attribute to be, we capture the error and set the value to 0, which is what goes into the attribute. Otherwise, we accept the value as correct if it can be integerized. I should point out here that this gate and this program is not necessarily a practical thing. For example, if we were to pass a float, the int function would simply lop off any fractional value and turn, let's say, 3.6 into 3. So it's not a practical thing. I'm really just trying to illustrate in a simple way how we can validate values that go into our object and maintain its integrity. Having some sort of integrity gate is possibly more common in a constructor, since what we're doing is validating the object before even returning it for the first time. This is why the init method is so important. There are many things that a constructor might do. For example, if we were creating some sort of object that engages in networking, we could validate that a networking connection can be made. If we were creating an object that can communicate with the server to do things like start, restart, shut down, etc., we might begin by pinging the server to make sure that it's up and running. If our object's purpose was to parse a data file like an XML or CSV file, it might initialize itself by parsing the file and seeing if it is in the proper format. Any steps that need to be taken before an instance can be used, we would take care of in the constructor. So in this lesson, we learned how to implement a constructor for our instances. This gives us the opportunity to establish and validate attributes in the instance. We can also use it to do prep work necessary before an instance can be created. Remember, init is not necessary to be called, and it's not required. But if Python finds a method of that name in the class, it will call it every time an instance is constructed. It simply offers us the opportunity to initialize attributes in the instance and do other prep work at the time of construction. In this lesson, we're going to compare class attributes against instance attributes and show how the instance can access either. You may have noticed, and we did briefly discuss, that variables defined in the class, as well as attributes set in the object, are both accessed through the instance using object.attribute syntax. In this example, classy is a class variable. It's a variable set in the class. And insty is an attribute set in the instance. You can see that the instance has access to both its own attribute, insty, and the class variable, classy. Consider what happens when we say dd.classy or dd.insty. In other words, object.attribute or instance.attribute. Insty was set in the instance. It's an instance attribute, and classy was set in the class. And we can call this a class attribute. Since we can access both instance attributes and class attributes through the instance, there must be some kind of name lookup mechanism. Let's do an experiment. Let's break encapsulation and just set an attribute in the instance, and let's call it the same name as the class attribute. Okay, we've set a class variable, which we also call a class attribute, classy, and we've given it an identifier here. We create a new instance and we print dd classy. Let's see what we get. Class value. That's the first thing we see. Then we set inst value in the same attribute in the instance. In other words, instead of just reading it, we're actually setting it. Now we print it and we see what? Inst value. No surprise there. If we delete dd classy, we're deleting the attribute from the instance. We can then print dd classy again and see we go back to class value. So in other words, the first time we printed it, it read it from the class. The second time we printed it, it had been set in the instance. And finally, after removing the instance attribute, we print it again and it retrieves it from the class again. This should pretty much prove that there's an attribute lookup order, first in the instance and then in the class. Now, I want to make clear that this isn't something that we would usually want to do. It would be terribly confusing to have a class attribute and an instance attribute with the same name. The purpose of this lesson is to show the relationship between class attributes and instance attributes, and in particular to show that when we request an attribute through an instance, it looks for that attribute in the instance first and then in the class. We call this an attribute lookup order. So this completes our understanding of classes and instances. These lessons have been less about practical application and more about the underlying mechanics of classes and instances. There's plenty more to discuss concerning classes, but now we have a basic understanding of how classes and instances behave and interact. In this lesson, we're going to see how class data relates to instance data and start talking about situations in which we might want to store data in the class. We've seen that we can store some data in our instances, but that we can also store some data in the class itself. When we're designing our classes, we'll decide which data belongs in each instance and which data should be stored in the overall class. As we saw, an instance can access class data. That means, of course, that if we create multiple instances, they will have access to their own individual attribute values, but they'll also have access to the same class data. Therefore, class data will be data that is intended to be shared among instances. The classic example of the use of class data, which is often employed in academic courses, is the instance counter. Note first that we have a class variable, count, which is set to 0 at the outset. As you know, this class variable is also a class attribute, and it's accessible through any instance created from the class. What's going on when we create a new instance counter object? It looks like the constructor requires a value, an integer, which we're passing each time we create a new instance. And as you can see here, we're creating 3 new instance counter instances. And we're storing it in the instance in the val attribute. Now look at this next line. Instance counter.count plus equals 1. Plus equals, I'm sure you know, means that we're saying instance counter.count equals instance counter.count plus 1. We're simply adding 1 to the current value of this attribute. We're starting with the class name instance counter, and then we're using it as an object in the object.attribute syntax to increment the value of count. This count is the same count that we're seeing up here. It's not just a class variable, it's a class attribute, and it's accessible through the class name. But this time, rather than using the instance, the class itself is standing as the object. Does this mean that the class is also an object? Let's check it out. I'll just create class, and I'm going to do this right here in the Python prompt. I'll create one of these empty classes, you might remember. I'll print my class. It looks like some kind of object. It's identifying itself as a class, and I can tell you that it is a class object. As we mentioned before, everything in Python is an object. Does this mean it has attributes? Let's find out. That looks like an attribute list to me. They're all private or magic attributes, but they're still attributes. I wonder if we could even set a value in it. What's also interesting is that once you set an attribute in the class object, or in any object for that matter, the directory of attributes actually includes the attributes that we set. But here's a question. If we're in the code for the class, and we're referring to a variable that was set count equals 0, why then do we have to qualify it with the class name when we're trying to get the value out? The answer has to do with global variables. If you've taken a course in beginning Python or you've read up on it, you may know about globals. They're the variables we set in the main body of the program. For example, if I were to just say var equals 10, that's a global variable. If Python didn't require that you qualify this variable name with the class name, as we're doing here, then you wouldn't be able to access global variables from within the class, and that's something you might conceivably want to be able to do. Therefore, any variable set in the class needs to be accessed using object.attribute syntax, and we're using the class object itself to access this attribute. Let's look at the output. We're looping through a tuple of our instances and calling getVal on each. For object A, B, C, I've created a tuple of the 3 instances, and as we loop through these 3 instances, I'm assigning the instance to obj. It's really just each instance in turn. So I'm basically saying a.getVal, a.getCount, then b.getVal, b.getCount, etc. And as we do that, that gets us the number that we set in the constructor. You can see that A was set with 5, B with 13, C with 17, and as we print getVal, we're getting 5, 13, and 17. But with each instance, we're also calling getCount. And what goes on with getCount? It simply returns the value of the class variable, or the class attribute count. So you can see that each instance has access to its own data, which was set in the instance itself, as well as the class data, which was set in the class. Ask yourself why we're seeing 3 when we print count. It would be because we've run into this statement 3 times, and why would that be? It's because every time we create a new instance, init gets called automatically. What this is effectively doing is counting the number of instances that were created. Now, one other thing we should mention is that although we're calling getCount, and that's getting us the class name.count, could we access this value through the instance? And of course, the answer is yes. As we know from an earlier lesson, when we ask for an attribute from an instance, it looks first in the instance and then in the class. Let's replace this with an access of count straight from the object. Sure enough, works in the exact same way. I'm going to go ahead and make a change here to make sure that I'm not seeing the old output. And there it is. So in this lesson, we've looked at an example of class attributes, what we also call class data, and how Python allows us to set values in the class that are accessible through each of the instances, as well as through the class itself. What we're building here in these lessons so far is an understanding of the framework that software developers worldwide use to build code that we use every day. As we learn more, we'll start to see ways in which we can apply this framework to our own code. But there's more to learn about the object-oriented paradigm, so stay tuned. In our first assignment, we'll create a simple class that acts a little bit like a list, with certain limits on its size. Here's how your class should behave when your solution is complete. As you can see, I've placed the maxSizeList class inside a file called assignments.py and imported it through the module. If you're at all unclear on setting up a module, you can simply define your class in the same file where you run this code, in which case you don't need the import statement. Here we've replaced the import statement with the class definition, and your code would go here where we see the ellipsis. Once maxSizeList is available to us, whether from module import or because it's in the same file, we're demonstrating its features here by creating 2 maxSizeList objects or instances, and by passing a different integer to each constructor. Notice the correspondence between the number of elements returned by getList and the integer value that we passed in the constructor. In other words, we passed the integer 3 to the constructor that created the object assigned to A, and getList called on A returns 3 elements. And we see the output here at the bottom. We pass the integer 1 to the constructor that creates the object to B, and getList called on B returns 1 element. The integer argument passed to the constructor will determine the maximum size of the list being held by the maxSizeList object. So what attributes does each instance have to hold? Certainly it needs to have an attribute that is a list. Now so far, we've seen attributes that only hold integers or strings. But an attribute can hold any object in the same way that a variable label can be associated with any object. As you can see here, we've created a dummy class that simply sets 3 attributes in the instance. And we're just demonstrating that any type of object can be set as an attribute in the instance. In this case, we're using an integer and a string and a list, each as values or objects that get associated with the instance in its attributes AA, BB, and CC. And here at the end, we're printing the last attribute to show that it's the same list. So having established that our instance can hold a list, see how getList could produce a list that's obviously reading from one of its attributes. And we've been updating the attribute with every call to the push method. But what other attributes would the object have to hold? Well, it would need to know what its maximum size is. Because as you can see from the demo, if we try to add an element that would make the size of the list greater than its maximum size, it drops an element from the list. And that's what's going on here as we pass 4 elements to the A instance and 4 elements to the B instance. In both cases, we reach the maximum size that that instance can hold, and so we're only seeing the last elements that were pushed. In other words, the initial elements get dropped when we reach the maximum size. I'm going to show you how we can manipulate a list in the way we might need for this assignment. I'm going to go ahead and add a couple of elements to a list that I created here and show that the elements got added. We can also see the length of the list by using the len method. This is all pretty basic stuff, but I'd like to make sure that you're up on what we're doing here. To remove an element, as you may know, we can use the pop method. Pop returns the element that was removed, and you can see when we look again, that element has indeed been removed. Beyond these hints, you'll need lessons we learned about the constructor for initializing an instance, and setter and getter methods for setting attributes in the instance and getting attributes from the instance. You'll find a text version of this assignment in the working files, and we'll look at the solution in the next lesson. Here's my solution to the problem posed in the previous lesson. I want to emphasize that just because it's my solution, that doesn't make this the best solution. This is a pretty simple problem, so there are probably a few other ways to do this that would be simpler than this solution. But always keep in mind that there's usually more than one way to do something. Generally speaking, when we evaluate code, we want to think about clarity first. Maintainability is also extremely important when you're looking at code and deciding whether it's well written. Consistency of syntax and a variable naming, and this gets back to clarity again. And then brevity. These are the qualities I consider the most important when I'm evaluating other people's code. And that's because Python is designed to have clear syntax, to be highly collaborative, which means that other people will be reading your code and trying to understand it, and for a high level of maintainability. Some Python programmers are concerned with time efficiency and memory efficiency, and it's something we'll address later on in this course as well when we look at the timeit module for profiling code. But I do have to say that if time efficiency and memory efficiency are your most important concerns, you might want to consider another language, because Python is certainly not the most efficient language, certainly not as time or memory efficient as Java or C or C++. So this is why I emphasize clarity and maintainability first. The first thing we need to do is initialize the object. We create an init method to do that. As I intimated in the assignment, one solution would be to use two attributes. One to store the list itself, and this is done with the list attribute, and one to store the maximum size, which we're doing here in the max size attribute. And of course, max is being set by the argument to max size list, because the purpose of this is to allow us to declare a maximum size at the time we create the object. The next is the push method, which adds a value to the list held in the object's list attribute. The value being added is the object being passed to the method obj, and we simply passed obj as the argument to a call to the list's append method. We took it from here and we brought it to here and appended it to this inner list which we had declared up here. Then after appending, we check to see if by doing so we've exceeded the value of the max size. Perhaps the list is now too big. So we check if the length of inner list, now that we've added the new object, is greater than the max size which was set at the top. If so, we remove the element from the list. And by popping 0, we're saying remove the 0 element or the first element from the list. We're not bothering to capture the return value of pop because we don't care about the element anymore. We're discarding it. Now, just to be extra clear, this method might seem a little strange to you because the syntax looks funny, but just keep in mind, we're simply appending to the list that we created in self-innerlist. So self.innerlist gives us the list, object.append is the method being called on that list. Finally, getList returns the inner list. In the test code, we're printing this value by calling getList and placing it as the arguments to print down here, a.getList, and we're passing it as an argument to print. That simply means that when getList returns self.innerList, which is the list we were appending to, we're simply printing that list. And you can see the output down here. So the purpose of this was to have you create a class that can produce objects that store attributes. If you found that your values were off or things weren't working quite the way you expected, make sure that you're always dealing with the object itself. If you're declaring a variable outside the object and maybe making a list and a variable up here, that would not be encapsulated instance data. That's class data. And if you're getting strange effects, it might be because you're doing that. That's one possibility. And now let's start a new section on inheritance and polymorphism. In this lesson, we'll look at inheritance, which is the second pillar of object-oriented programming. As you know, there are 3 pillars in object-oriented programming, and this is the second. You'll remember that encapsulation is the facility by which we can store data in an object and provide for data integrity by using getter and setter methods. Inheritance refers to a new feature that we'll look at now, the ability to have one class inherit the attributes of another class. As you can see, we have 2 classes, date and time. Now, they do precious little, but they do make inheritance clear. Look closely at the class definition. Specifically, in the parentheses, we have object in the arguments list to date and date in the arguments list to time. What this means is that time inherits from date, and date inherits from a class called object. We mentioned object before. It's a built-in class provided by Python, and it confers upon date some specific attributes, which we're going to discuss in a later lesson. But the thing to pay close attention to is the fact that time inherits from date. Now take a look below. We create a new date object, and we call getDate on it. Then we create a new time object, and we call getTime on it. But then look, we're also able to call getDate on the time object. It is specifically because we placed the date class name in the arguments list of the time class definition that we're able to call a date method on a time object. And we can illustrate that by trying to run the program when time does not inherit from date. We'll get an error. Time instance has no attribute getDate. But if we add date back into the inheritance list, we'll find that it works again. And that's because of inheritance. So, at base, inheritance is simply another level of attribute lookup. Remember that when we ask an instance to give us the value of an attribute, or to call a method using object.attribute syntax, we're initiating a lookup that proceeds from place to place in a particular order. So, this gives us an opportunity for a very small quiz in which I'll try to trip you up. As we know, when we ask an object for an attribute, it uses a lookup hierarchy. When we say object.attribute, in this case, let's say tm.getTime, that's an attribute lookup. So where is the first place that the time object tm looks for the attribute getDate? Because we're simply asking the tm object to find the attribute getDate. Where's the first place? The answer is in the instance itself. You may ask, is this true even when we're accessing a method? After all, methods are located in the class. It's a method, shouldn't it look in the class first? The answer is no, because Python doesn't care whether this attribute is a method object, a string object, a list object. It really doesn't matter. We're doing an attribute lookup. So in every case, Python will follow the lookup order to try to find things. So there are now 3 places where Python looks for an attribute. In the instance, then in the class to which the instance belongs, and then if that class inherits from another class, Python will look in the parent class. Object-oriented programming is never short on terminology, and it even has synonyms for its own terms. Take a look at this list and just read these terms as rather common sense descriptions of what's going on. There's no need to get hung up on them. When you encounter them again, just use your common sense. An inheriting class can be known as a child class, a subclass, or a derived class, and that would be my class in this example. An inherited class, like your class, which actually is also a child class of object, but in this case the parent class of my class is also known as a base class or a superclass. And of course you'll find all these terms in the glossary. So in this lesson, we learned about inheritance, which is really a very simple mechanism for sharing attributes between classes. We learned that there are three places where an instance might look for an attribute when we use the object-attribute syntax to access an attribute. And we'll see more examples of this as we go forward. In this lesson, we'll take a closer look at some inheritance examples, both one traditionally used in textbooks on the subject, and I'll also share a practical example from my early days in coding. Here we have a class, animal, that inherits from object. For now, you can know that object is a built-in superclass from which all new style classes inherit. Now look at the definitions for dog and cat. As you can see, they both inherit from animal. So what are animal's attributes? There are two variables defined in animal. They're the two methods that we find here. The fact that they're function definitions doesn't make them any different from any other variable. And of course, being variables in animal means that they're also animal's attributes, and they'll be inherited by dog and cat. Now look at dog. We have one attribute, one method defined, fetch, and in cat, swat string. Great, now let's look at the code beneath the class definitions. We create a new dog object, and we create a new cat object. Since these are both pets, we've decided to give each animal a name. What happens when we construct the dog object? Does init get called when we create a dog object? As far as inheritance goes, init is not really any different from any other method. When we construct a dog object, the first thing that Python does is look for init in the dog class. But because it isn't there, Python then checks to see if dog inherits from any other classes. When it sees that dog inherits from animal, it looks for the init attribute there. Sure enough, there is an init in animal, so Python calls init there. Then here's another question. What is self in this case? Is it a dog instance or an animal instance? It's a dog instance, the same as if the init was in the dog class. And the reason for this is that we're asking Python to create a dog instance, so it creates one and it passes it to init. Now init happens to be up in animal, but that doesn't really make a difference. We're calling animals init with a dog instance. And of course, this sets an attribute in the instance. Our code goes ahead and calls methods on these objects. We call fetch on the dog object, we call swat string on the cat object, and we call eat on both the cat and dog objects. So the reason we've organized the methods in this way is because we know that dogs will fetch and a cat will swat string. So we've put these methods in their respective classes. But we also know that all dogs and cats eat. In other words, all animals do eat. So we've put eat up in the animal class. And this makes the most sense. And it's one of the reasons inheritance is so valuable. We're able to avoid duplicating code if we can arrange our classes in an inheritance hierarchy that makes sense. And I can just run this to prove that it works. As you can see in the end, we're calling swat string on our dog object, and then that results in a failure or an exception. Dog object has no attribute swat string. But we are able to see that we can call eat on both the dog and cat object. Here's an example from my own experience. I first learned how to code during the original internet boom in the late 90s. I took a certificate course in Java, I did a couple of freelance projects, and then I landed a job at a magazine publisher who had decided to create online magazines. One of the online magazines was a travel guide, and years before Facebook, they devised a website that would let you upload pictures, descriptions, blog entries, all relating to a trip. It was a way to share your trip photos and your experiences with your friends and family. You could just say, go to this website, and you'll see all my trip photos. This was my very first Java project as a programmer, and I was excited. They asked me to create a Java class that would allow the user to upload photos, and I was to create thumbnails and a slideshow. My team lead told me that my class would fit into a hierarchy of classes that inherited from one another. He told me to inherit from a class he had written. We'll call it Travel App. I was writing in Java, but I've translated it in this pseudocode to Python so you can follow along. Since my class would be inheriting from his class, I'd be able to make use of all the methods that he had defined, like getUsername, which returned the current user's username. But there was more than that, because this entire app that we were writing was written to fit within and inherit from an application server, which is a program designed to run web applications. So the Travel App class inherited from App Server, which was the application server. That was responsible for handling the web request and database calls and that sort of thing. So in effect, we were collaborating with a developer we had never met who had written the app server code. And inheriting from that code meant that we could write an app that really fit the other code like a glove. And so you can see again how inheritance promotes collaboration. Now I've color-coded this code to show the relationships. You can see, for example, that I'm calling getUsername, which is actually a method that's in the class from which I inherited. You can see that this method, getUsername, has code that calls a method that's in the AppServer class. And in fact, I myself can call a method from the AppServer class. It's all done through inheritance. I'm inheriting from TravelApp, TravelApp is inheriting from AppServer, and so the lookup goes. When I call acceptsImages, which was a method that told me whether or not this browser can display images, Python looks for this attribute first in the instance. Then, if it can't find it, it looks in the inheritance hierarchy to see where I'm inheriting from, TravelApp, and looks for acceptsImages there. Not finding it, it again looks in the inheritance hierarchy, AppServer, and then looks in AppServer for acceptsImages and finds it. If it didn't find it, of course, it would be an error. But because we know that acceptsImages is part of the inheritance, we can call it without worrying. Through documentation, we were able to see exactly what was available to us when we inherited from a particular class. And we were able to work together on very complex code by carefully documenting what our own class did. So in this lesson, we saw another example of inheritance, and we started to see the value of this important pillar of object-oriented programming. We also got a taste of what an inheritance hierarchy might mean to a team working together on a collaborative project. And of course, we'll see more examples as we continue to explore. In this lesson, we'll look at polymorphism, the last of the three pillars of object-oriented programming. Polymorphism means many shapes. This refers to a design in which objects of dissimilar types can be treated in the same manner. More specifically, it refers to two classes that have methods of the same name. We call this a common interface because we can call the same method on either type of object. The classic illustration is between two classes that inherit from the same parent class. Let's go back to the animal metaphor, and then we'll see how some very familiar Python classes are polymorphic. This is our original animal, dog, and cat example, but we've added a showAffection method to both the dog and the cat classes. Note that these aren't inherited methods, but rather two entirely different methods with the same name. In other words, we don't see showAffection appear at all, and yet they appear in both dog and cat, which means they're really independent methods. Since we call them the same way on each object, we can say that the two objects have the same interface for showing affection. But note that what happens when we call the method on a dog object is very different from calling it on a cat object. Let's run the code. When we call showAffection on a dog object, Rover wags his tail. But when we call it on a cat object, Fluffy purrs. And you can see that we've just put a random sampling of new dog and cat objects in this list. And for each one of those objects, we're calling showAffection. And so that's why we see each one of these animals showing affection. Even though we're calling the same method on each of the objects do entirely different things. Conceptually, they're doing the same things, but it's really very different. What's convenient about this is that as long as we know we have an animal object, and as long as we understand that the contract is that an animal will have a showAffection method, we don't really need to care what type we're dealing with. We can just call showAffection and it'll do the right thing. This feature is more of a technique than anything else. Note that it doesn't depend on any magic functionality, and it enhances our expressiveness in the language. We can design not only a single class that does something, but a family of classes that do the same thing, possibly differently, but they can all be seen as able to do that thing. In this case, as long as the user of the classes knows that he or she is dealing with animal objects, it shouldn't be important what particular animal is being passed, only which attributes are understood to be available. If errors should occur or the wrong type be used, exceptions can be used to handle errors. Being able to work with different types, to call methods without checking that it is possible ahead of time, and to handle errors using exception handling, which we'll discuss shortly, is called duck typing. In other words, as we showed before, we don't care what type of animal we have. we just call show affection on it, and we trust the interface contract. That is, that we know that every animal will implement show affection to do the right thing when we call it. The term duck typing comes from the saying, if it walks like a duck and it quacks like a duck, it must be a duck. In other words, we're going to try to do the thing that we expect this object to be able to do, rather than check ahead of time to see whether it's possible. But checking the type ahead of time is generally considered unpythonic, and this will become clearer as you become more experienced. We generally do the thing we want to do, and we trap errors if they occur. And we'll discuss this further when we discuss exceptions. Python itself has classes that are polymorphic, and this has been happening pretty much right under our noses. The len function can be used with multiple objects: strings, lists, tuples, dictionaries, and sets. And here you can see in the Python prompt, I've passed a string, a list, a tuple, and a dictionary to len. And it's giving me the right answer each time. 5 characters in hello, 3 elements in 1, 2, 3, 3 elements in ABC, and 2 pairs in A1 and B2. But you may say, len is a built-in function. How's that polymorphic when it isn't even a method? Allow me to show you a little magic. The truth is, built-in functions, the way we normally use them, are really just an easy way to write something. In other words, we're allowed to use them as built-in functions because it's convenient for us. But the truth is, when we do use built-in functions, they translate into a method call on the object being passed. Let's look at len again with a string. Here we've assigned a string to the label var, and we're taking a len of var. But this actually translates into something else. It's a method of the string object. Remember, every time you do a dir on any object, you get a bunch of methods. I should say attributes, not necessarily methods. But in the strings case, they're almost all methods. We have a bunch of ones that we use directly, but then there are ones that we're actually using indirectly and we're not aware of, and len is one of them. And there are other built-in operators too, like the in operator, which, as you know, in can be used to see what's inside a string. That translates into a method called contains. Or the concatenation operator, the plus sign. That translates to a method called add. So if it's true that len with a string calls the string method len, then it must also be true that the other objects that we can use with len also implement this method. As you remember, we were able to use len with a string, a list, a tuple, and a dictionary. So let's check out the dirs for those. Do we see len? Absolutely, there it is. Let's try it with a dictionary. Does it have a len? Certainly. A lot of what we do in Python actually translate into method calls. And since those method calls have the same names, that is, the same interface, they're all polymorphic. This extends to the plus sign, which is useful with integers, floats, or strings. The multiplication operator, which can be used with 2 numbers or with a number in a string, and the list goes on. So again, when we say polymorphic, we're talking about the same interface between 2 objects that do conceptually similar things. So in this lesson, we learned what polymorphism is: a conceptual connection and an identical interface between 2 objects. Again, this allows our design to be more expressive and in places more readily clear and understandable to the developer who's using our class. So it's a very important pillar of object-oriented programming. In this lesson, we'll discuss how and why we might inherit a constructor from a parent class, in addition to any constructor we may want to have in our own class. You'll remember from our first animals example that init was located in the parent class up here. Because the child's class, dog, didn't have an init method, Python used the inheritance attribute lookup to find init in the animal class. In other words, when we created a dog object, it looked for init in dog, didn't find it, then looked in animal and found it there, and then called it there. As our class design becomes complex, we may wish to initialize an instance by first processing it through the parent class constructor and then through the child class constructor. Let's look at an enhanced example. Here, we're giving all animals a name, and all dogs a particular dog breed. We call a parent class constructor with super, as shown above. So now dog has its own init, but the first thing that happens is we call super. Now super is a built-in function, and it's designed to relate a class to its superclass, or its parent class. In this case, we're saying, get the superclass of dog, and pass the dog instance to whatever method we say here. the constructor init. So in other words, we're calling animal.init with the dog object. And you may ask, why don't we just say animal.init with the dog instance? We could do this, but if the name of the animal class were to change sometime in the future, or if we rearrange the class hierarchy so that dog inherited from another class first, let's say the quadruped class, and we preferred now that we call that constructor instead, we'd need to go in and change the name in the class. Using super in this case allows us to keep things modular and easy to change or maintain. So in this example, what we're trying to do is use general init functionality along with more specialized init functionality, and we're using them together. In this case, we want a dog to have a name, just like we want all animals to have a name. But we also want a dog to set its own breed, which we're doing in the specialized init. So we're able to combine general init functionality with more specific init functionality. Again, this gives us the opportunity to separate common functionality from more specific functionality, which can eliminate code duplication and relate classes to one another in a way that reflects the system's overall design. So in this lesson, we took a brief look at the super built-in function and how it can give us access to a parent class's attributes, most notably its methods. And we saw how init can be used both in the parent class and in the child class as a way to combine generalized functionality with specific functionality. This use of super is another facet of the toolkit that you'll be able to use when you're designing your own classes and class systems. In this lesson, we'll look at something called multiple inheritance, which refers to the ability of one class to inherit from two or more other classes. In a complex inheritance scheme, a class may inherit from multiple classes, and any of these parent classes may themselves inherit from one or more other classes. As we saw in a previous example, Python climbs the inheritance tree looking for an attribute that's been requested to be read from an object. Python will check the instance, then the class, then any parent classes, and then what we may call grandparent classes to find the attribute. In the case of multiple inheritance, one may ask in what order classes are searched, depth first or breadth first. For example, we create a D object in this class hierarchy. D inherits from B, and it also inherits from C. Instead of putting one class as the parent class, we put two. Not all languages support this, but Python does. So after creating a D instance, we call doThis. The confusion can come from the fact that we've implemented doThis in the A class, which is a grandparent of D, and the C class. And one of two things is possible. If we call dinst doThis, first place it's going to look is in the instance, then in the class, then in a parent class. It'll look for it in B first, because it's the very first thing we see in the inheritance tree. But what next? Would it then look in B's inheritance list and find it in A? Or would it then go from B to C and ask for doThis in C? So is it depth first, which would be up here, or is it breadth first, meaning it'll go to B and then C? In this particular case, the answer is A. By default, Python will use a depth-first search for an attribute. We'll say D inherits from B, B inherits from A, then back down to D. Next item it inherits from is C. So the method resolution order, and this is a new term, is D, B, A, C. Now this is really important in larger class systems, because we may have a complex tree and we may have the same method implemented in multiple classes. So if you're not aware of this method resolution order, you might find that the doThis call happens in a different class than what you were expecting. In fact, we can have Python show us the order in which attributes are checked by using a special method called MRO. We'll just apply that to class. We do have to print it. So here we can see the method resolution order that Python uses specifically. When we call doThis on a D instance, it looks first in D, then it looks in B, then A, and then C. In other words, a depth first lookup. However, things get a little more complicated if the same class appears in two other classes' inheritance lists, which creates an ambiguous order. This is the infamous diamond inheritance pattern. Here we have D inheriting from B and C as before, but B also inherits from A, and C in addition inherits from A. So if it's a depth-first search, you'd probably expect D, then B, then A, then finally C, as we saw in the previous example. However, because of the ambiguity, which basically would say that the order should be D, B, A, C, A, it's considered ambiguous. Starting in Python 2.3, a slightly altered method resolution order is used. Its only difference to the depth-first search that we discussed earlier is in the cases where we have this multiple inheritance in which more than one parent classes inherit from the same class. In other words, to remove the ambiguity of D, B, A, C, A. The way Python handles the ambiguity is to remove earlier appearances of multiply referred to classes, in other words, A. So the depth-first tree would say D, B, A, C, A. But because A is repeated, it removes the earlier occurrence of A. So the method resolution order in a diamond-shaped pattern is D, B, C, A. So here's this diamond-shaped pattern rendered in code. As you can see, D inherits from B and C and C each inherit from A. And then down here, we're going to print the method resolution order. We can see what happens, and we'll also get to see which method do this is getting called, since it appears in both A and C. As you can see, this time C wins, and the method resolution order is D, B, C, and A. Now this looks a little bit like a breadth-first search, but it isn't. Instead, there's just an additional rule that's added to the depth-first search. And again, that rule is, if the same class appears in a method resolution order, the earlier occurrences of this class are removed from the method resolution order. As you can see, it's D, then B, then it would be A, but because A appears twice, it's removed from the order. So Python moves ahead to C, and then finally A, which of course is a parent class of C. It's important that I mention here that the method resolution order we're talking about is one that was introduced for new style classes in Python. New style classes must inherit from a super ancestor class called object, and this is what we've been seeing all along. All of our classes have been new style, and we're going to discuss this in more depth shortly. So in this lesson, we looked at multiple inheritance, in which any class can inherit from multiple classes. The reasons for doing this have to do again with code sharing and reuse, the effort not to duplicate code, the maintainability of code. Python chooses this additional feature, which as I mentioned is not available in every other language, to give us more design options and creativity. In this lesson, we'll look at two special kinds of methods that are alternatives to the methods that we've seen so far. The methods that we've seen so far are called instance methods because they're designed to work on the instance. Here's a familiar example, and as you can see, we have 4 instance methods. How do I know they're instance methods? Because the instance is the first argument to each one of them. And as you know, this is an automatic behavior when calling a method on an object. We say object.method, and it passes the object as the first element. The object, the instance, gets passed automatically to an instance method. And because of this automatic passing, we sometimes call instance methods bound methods. And that's because the instance is bound to the method. It works with the method. And this is very useful. Oftentimes what we want to do is modify the object, that is, set a value or get a value. The new special methods that we're going to look at in this lesson are called class methods and static methods, and they're not bound to the instance. And if you think about it, a class is really a library of functionality that's associated with the instances that it produces. But some of the functionality might not actually have to do with the instance itself. Some of the functionality might be relating directly to the class itself, dealing with class data. For example, the instance counter, count attribute, which we've discussed earlier. Or we might even have some methods that are just utility methods. They're not designed to work with the class or the instance. Since the instance is not required to use these things, we're probably going to want to have these other types of methods, which again we call class methods and static methods. Class methods for working with the class, and static methods for working independently of either the class or the instance. So let's look at this method getCount. Is this a bound method or an unbound method? Is this an instance method or is it a static or class method? Well, it takes the instance as the first argument, and that's automatically passed. So it's a bound method. It's an instance method. But what are we doing in this instance method? Let's run the code. As you can see, for each of the 3 instances that we created, 3 instance counter instances or objects, and we passed an integer to each one of them. We're getting the value that's stored in the instance, and we're also calling getCount on each of the instances. So what does getCount do? We have the value of the object stored in the instance. That's from getVal, and that was the value that we set in the constructor. But count is 3 for each one of them. Let's see what's going on. Return instance counter.count. And instance counter.count happened up here, where we're incrementing a value for each time we create an instance. So when we call getCount, is the instance necessary? It doesn't look like it. It's not even coming into play. So this is where the class method comes in. The method that's intended to work with the class, as getCount does. What we can do is replace self with CLS. Now the label itself doesn't make a difference. This is a customary label when talking about the class. But we haven't really affected the functionality of the method. It's still a bound method, and we're still going to see the instance assigned to CLS. And of course, we can't use the word class because it's reserved. You can see it's used in a class definition. What we'll do to change the method into a class method is put a special modifier above the method in question. This is what we call a function or method decorator. A decorator is a special function that can modify functions. We don't have the space here to discuss the mechanics in detail, but suffice to say that if we apply the class method decorator to a method, we can cause that method to pass the class automatically when called instead of the instance. Let's try it. Now, you may observe that the functionality is exactly the same. We didn't really need to change this function or this method to make it a class method for it to work. However, it's important that we make sure our code is as logically designed as possible. Again, if we leave this as an instance method, it implies that we intend to work with the instance, but that's definitely not the case when it comes to getCount. So it's absolutely correct to make this into a class method because it works with the class. And in fact, one thing I forgot to do was simply to use the class object, which is now being passed to getCount, as the object from which we'll read the count attribute. Let's try it again. Okay, again, the same thing. But now, because it's a class method, it's very clear to anyone reading this code that I intend to work with the class. I intend to work with class attributes. And count, of course, is a class attribute. It would have been misleading to keep it as an instance attribute, even if it does work the same way. Of course, in addition to that, I can also use the class itself to call the method. And this should work as well. Of course, it would work even better if I printed the value first. You can see I added the 3 right there at the end. Another decorator that's available to us is called a static method. I've changed the example here to include a new decorator and a new method called filterInt. FilterInt is being used in the constructor to make sure that the argument passed to the constructor is an integer, which is of course what we're doing here, but we'd like to make sure. Once the value goes from the constructor call up into the constructor, it's passed to the filterInt method, which takes the value and makes sure that it's an integer. It has to be of the type integer, and that's what isInstance is doing right here. If it is, the value will be returned, and then it'll be assigned to the attribute val. But if it's not, it'll return 0, which means that if we attempt to set a bad value in the attribute, we'll see 0 instead, and this is similar to previous examples that we've seen. Let's run this code and see what we get. Great, it's working the way it should so far. But let's change it then and put in a bad value. Great, as you can see, the last instance counter, which we passed a bad value to, has now stored 0 in its val attribute. The reason we decorated filterInt with the static method decorator is because it's neither a class method, which would work with the class, or an instance method, which would work with the instance. Instead, it's just a utility class. It does something useful. It belongs in the class code because it works with the class code, but it's neither an instance nor a class method. So we make it a static method. And notice, self is missing. The value that gets passed is simply passed directly, with no implicit argument added. In other words, it's not a bound method. It's a static method. You may observe that we are actually calling filterInt on the instance, but the instance isn't getting passed, as I mentioned. Again, we could have made it an instance method, and it wouldn't really have been a problem to do so. But once again, we don't want to be misleading. If the method is intended just to be a utility method, and it doesn't need the instance to work, we shouldn't be implying that it does, which is what an instance method really does. Instead, we'll use static method, and now the method doesn't require any implicit argument at all. So in this lesson, we looked at class methods, static methods, and function decorators, which we can also call method decorators. We saw how decorators modify the behavior of our methods, and we also saw how classes can contain class methods and static methods, as well as instance methods. Thus, we can build methods that are narrowly focused on their own scope, and whose meaning is clear when read by users of the code. In this lesson, we'll look at abstract classes, which are blueprints for how subclasses should be designed. You may remember that when I first described classes, I called them blueprints for instances. A class defines the attributes that will be set in an instance, as well as defining attributes that the instance can access, the class attributes. So a class really is a kind of a blueprint for an instance. But when we're working in a collaborative environment with other developers who are creating classes that'll fit into a larger hierarchy, we may want to define a class that indicates and enforces what methods a subclass should implement, and we call this an abstract class. Let's go back to our getter and setter class. If we were working on a team, or if we had designed a library that requires other members to contribute classes, we might want to require that the developers implement certain methods. In this example, we have a class that sets a value and gets a value. If that's the basic interface that we'd like other developers to implement, we can ask them to subclass or inherit from our class, and we'll want to declare our methods in such a way that defining these methods is required in any subclass. So let's do that now. The ABC module imported up here provides facilities for creating abstract base classes, which are classes that are not designed to be instantiated, but only to be subclassed. In other words, we don't create a getter-setter instance. We're only going to inherit from getter-setter. One way to create an abstract base class is to make use of a meta class, which is basically a class that can define other classes. I'm not going to go into too much more detail, but basically, when we assign ABC meta to the meta class magic attribute, we're basically saying that this should be defined as an abstract base class. And we'll see what sort of rules are applied here in a moment. Then, above each of the methods, we place a decorator, indicating that these methods are abstract methods. Now we've created the contract. We've created the template from which other classes that subclass getter-setter will have to follow. And let's subclass getter-setter right now. Okay, now we've created a class that subclasses getter-setter and inherits from getter-setter. And we've established a setVal and a getVal method. In other words, we've fulfilled the contract that's shown up here. And we can run it just to show that it works. We're printing X, which is a myClass instance, and that's what we're seeing, a myClass object. So there's nothing really new going on here. What's new will be visible when we violate the contract. So let's do that. Let's not implement setVal. I'm just going to rename it setVals and then see if it'll still run. Now this error message is a little misleading. What it's actually saying is that it can't instantiate a myClass class because it hasn't implemented setVal. Clearly, if we go back to our original spelling and run it, Python has no problem with it. So you can see the stricture is there. If we omit any of these methods, we'll have a problem. Python itself will stop us. So you can see that as long as the developer follows our instructions and subclasses from getter-setter, the contract will be required and they'll have to set the methods that we define. The other stricture imposed here is that getter-setter cannot actually be instantiated. It's an abstract class, so it's not a concrete class, meaning it can't be instantiated. And we can try that right now and see that can instantiate abstract class getter-setter. So in this lesson, we got a basic overview of abstract basic classes. and we saw how they worked and discussed why they're being used. There's a great deal more to these classes than we're looking at here. This is really just an introduction. Unfortunately, there's far more technical background that would be required to discuss than would be appropriate for a video course like this one. But you do have enough to get started in a collaborative environment when you're called upon to use them. If you're interested in learning more, check out the ABC module online, where you can also find more detailed tutorials that describe the intricacies of abstract classes. In this lesson, we'll look at examples for different ways to design with inheritance, specifically examples where a child class can inherit the parent class method, override it with its own method, or possibly specialize the method, that is, do something more in addition to what the parent class does. These are all choices that we have when designing larger class systems with inheritance. So the objective here is to understand how this works and to be able to implement it in a basic way, similar to the examples that we'll use. We're not learning anything particularly new here, we're just seeing a slightly more detailed example to emphasize the choices that are available using inheritance. Unless you get deeply into designing larger class systems on your own, you'll likely first need this knowledge when you join a programming team that is working on such a system, or you may encounter it when working with a publicly available library such as Google's App Engine or the Django content management system. Now here's a longer example than any we've seen so far. We're going to look at it in pieces, but here's the complete code for the three classes. We have a getSetParent, which inherits from object. We'll go over that later. And then we have getSetInt and getSetList. These are both inheriting from getSetParent. So we're going to see examples in which methods can either override, specialize, or perhaps just defer to methods in the parent class. So here we have the parent class, getSetParent. And as you can see, we've defined one of the methods as an abstract method, showDoc. You may have noticed this from last time. Abstract methods don't do anything, they simply have return at the end. Since we're using an abstract method, we've imported the ABC class, and we've established that the getSetParent will be an abstract-based class through the metaclass attribute, which means that getSetParent can't be instantiated directly. We can't create getSetParent objects. Then we have an init, a setVal, and a getVal. Again, very basic examples. The idea in this example is that getSetParent will stand as an abstract class, but that it will contain methods that can be inherited and used by the child classes. So our child classes have the option of either behaving the way getSetParent is already designed to do, or we'll be able to override or specialize the behavior depending on what we want each class to do. So in other words, this is a bit of a contract. Actually, the only required method is showDoc, but it's also sort of a library from which subclasses can start as a base to craft their own behavior. So here's our first child class, getSetInt. And as you can see, it implements only the two of the four methods defined in the parent, setVal and showDoc. And again, we know we're inheriting from getSetParent because we have getSetParent in the inheritance list. Let's compare it to getSetParent and see exactly what we're implementing and not implementing. getSetParent has getVal and setVal and init, as well as showDoc, which is an abstract method. And getSetInt has setVal and showDoc. So we've redefined setVal so that it checks to see if the value passed to setVal is an integer. The idea here is that getSetParent is just a generic getter or setter, but getSetInt is going to require that any values set will be integers. So look at setVal. It checks first to see that the value is an integer. That's what isInstance is doing. And we've seen this before. If the value is not an integer, we'll set the value to 0. Then we call super getSetInt self setVal, meaning it's going to look for the superclass of getSetInt, call setVal, and pass the instance as an argument. As we mentioned before when we discussed inheriting a constructor, this is a more modular way of saying call the parent. Rather than naming getSetParent directly, we're using the super built-in function to do this. So we call setVal with the value, which we now know is an integer, and setVal sets it in the attribute. This is similar to what we've seen before. We're just showing you another example of it. This is called specializing. The setVal method in getSetInt is specializing the setVal method in getSetParent. It's making use of the behavior in both. And then we're implementing the showDoc method because it's required of any child class inheriting from getSetParent. ShowDoc is simply designed to explain what this class is all about. And so this print statement is showing the instance's ID, which is an identifying value specific to this instance, as well as explaining what the instance is used for. It's not too important to get hung up on ID. This is simply saying, here's a getSetInt object, and it only accepts integer values. It's just explaining. By the way, when we see two strings right next to one another, even on separate lines, they're understood to be concatenated. I'm doing this for space reasons, but you can think of all of this as one string. And then the string method format allows us to insert values into a string. So I'm taking the ID for the instance and I'm inserting it where you see 0. The format string method is simply inserting this value into the string so that they can all be printed together. So basically, we've implemented what we had to, specialized what we wanted to, and allowed inheritance to take care of the rest. What happens when we call getVal on a getSet instance? What are we going to see? Since getVal can't be found in the child class that we're actually calling the method on, Python is going to look for getVal in the parent class, since getSetParent is in the inheritance list. This is review, but it's worth reiterating here. So here I've added code to instantiate a getSetInt object, then call setVal, then call getVal, and then call showDoc. And it works. Now let's look at a subclass of getSetParent that does even more specialization than getSetInt. This class acts like a getter-setter class, but instead of just storing and rewriting an integer every time we call setVal, it stores its values in a list and thus retains a history of all values that were set in the instance. So it does the same sort of thing as the other classes, and it has the same interface as the others as well, but it does something different. And because it does something different but has the same interface as another class, we can say that it's polymorphic. You can still take an instance of getSetList and call setVal, and it'll do something specific to that class, even though it's different than the other class might have done. And of course, to make this rather theoretical example work logically, we've also added its own special method, getVals, that will return all the values that have been stored. Let's bring up the code for running that and see that it does what it's supposed to do. We call getSetList with the integer 5. Instead of calling the parent init, it needs to set up a list. So what we're doing is creating a new list with a single value in it. We're then calling setVal10, setVal20, and then getVal. And getVal actually returns one element, but it looks like it just returns the last element that we set. Finally, we're calling getVals and seeing the entire list, and showDoc, which explains not only that this stores a history of values set, but shows the length of the list that has been created so far. And then comparing this to the parent, you can see that it overrides every element in getSetParent, which might cause you to ask, why are we even inheriting from getSetParent? Again, it's because of the contract. It's understood that we're going to have a method called showDoc implemented in getSetList. And overall, we understand that it's part of the getSetParent hierarchy, so it's a class that's understood to work with it. And later on, if we want to make changes and perhaps make use of getSetParent at some point, we'll be able to do that too. So in this lesson, we looked at a longer example demonstrating some of the options we have when designing class systems. We saw that a child class can override, or what is sometimes called overload, a parent class method, may choose to do additional work in addition to the parent class method, or it may simply inherit and use a parent class method by not implementing it at all. We also saw how a parent class may be abstract and require methods be implemented by child classes, in addition to having methods that can be inherited. Again, you're likely to encounter these first when working on a team or when working with Python libraries that you install from the outside world. Although these examples are very simple, they do pretty clearly illustrate some of the approaches taken to inheritance. You'll run into these concepts again when you start working in a larger class system, and eventually, perhaps designing your own. In this lesson, we'll look at another approach to working with multiple classes and an alternative to inheritance. It's called class composition. Inheritance has some critics who hold that the inheritance approach can lead to unnecessary restrictions, as it establishes dependencies between parent and child classes. They'll refer to this approach as brittle because one change in one part of the code can easily break it. The composition approach uses independent classes that can work together but aren't related in any particular way. There's a word sometimes used when discussing design, decoupling, which refers to allowing elements to be interactive but essentially independent. This goes back to the goal of writing maintainable code. When there are no dependencies, there are fewer instances in which a change can affect other parts of the code, which might also need to be changed to match. The basic concept behind composition is to use two or more classes that are not related by inheritance, but that can work together. Here's an example of a class that accepts a writer-type object that supports the method write. We're going to use two Python built-in classes, file class, which writes to files, and the string IO class, which writes to a string buffer. String buffer is just a string, but it's an object that we can write to as if it was a file. It's a little like concatenation, except that it's presumably more efficient. And it gives us the interface to a string that we would normally find in a file object, specifically the write method. So look how we're using the code. We're creating a file object and then passing it to write my stuff. Down here, we're creating a string IO, and we're also passing it to write my stuff. And then later, on the write my stuff object, we're calling write. So let's see how write my stuff works. The init method simply accepts the writer object, that is the file handle or the string IO object, and stores it in the object under the attribute writer. Then when we call write, it takes that writer, whatever it happens to be, and calls write on it. Notice that it doesn't check type. It doesn't check to see if it has a file object or a string IO object. It simply assumes that it can call the write method on that object, a very polymorphic behavior. So this is a decent example of composition. The chief advantage here is modularity. It really doesn't matter what type of object gets sent up to the write my stuff constructor. In fact, we could create our own class that produces objects that support the write method. Our own class could be writing to a database, to a network connection. It could be sending out a request over the web. It doesn't really matter to the write my stuff class, because write my stuff is simply taking whatever we send it and calling write on it. Again, polymorphic behavior, but it's also an example of class composition. The main point is that the different objects that we're working with are decoupled. They don't depend on one another. They are aware of each other's interface, though, and that's really key. As long as the interface stays the same on any of these objects, write my stuff can work with it. So we could make changes to any of these classes. Internal changes won't make a difference to write my stuff, as long as we can call write. So the benefit here is that we don't have to be worried about a class hierarchy. We don't have to ask how one class will affect another if we make a change. Instead, we just keep in mind the interface that we need to use, and we can use these classes together. Here's a more real-world example that is intended to work within Google's App Engine framework, although most of the variable names have been changed just for clarity. Google's App Engine is a web framework, which can allow you to create web applications that will be served out on Google servers, taking advantage of Google's security and massive scalability. The App Engine library takes care of all the core functionality of a web application. It responds to the request, it reads the cookie and the HTTP headers, and it prepares the response. Best of all, it scales. So if our application happens to become popular and millions of people start visiting, Google will scale with the demand. It also provides a measure of security that would be difficult to implement on your own. To build an App Engine application, we need only display the content that we want to see our application serve out. In other words, what appears on each page of our website, and Google App Engine will do the rest of the work. This application is very simple. It's simply going to have one page display a greeting and have another page display an FAQ. Now, the way we define what will be seen on each page is to create a class that App Engine will use to display it. The class defines what each page should display. Look at main page and FAQ page and see what similarities you can see. Both main page and FAQ page inherit from a Google class called request handler, and that would presumably give us additional functionality that Google might need when it uses our class. What we are defining is a get method for each one of these pages. Basically, all we're doing in this method is saying what should be displayed when someone requests this page. And over here, you can see we're defining the type of the text that will go out and the text that we'll see displayed. This is pretty much a complete application, even though I've changed the names and it won't actually work with App Engine. It does what we would need to set up a whole website with 2 simple pages. So here's a question for you. Where in this code are we creating a new main page instance or a new FAQ page instance? It's a bit of a trick question because neither of these classes is being instantiated. We're not creating a main page or an FAQ page instance. Instead, these classes are being passed to a Google function, which is then being passed to another Google function to run the application. What we're passing to this Google function is a list of 2-element tuples. The first element of each tuple says what the URL will look like in order for us to see the page. In other words, we go to mysite.com and there's nothing written after the domain. App Engine will display the main page. And if we visit mysite.com/info, Google will display the FAQ page. Now again, these instances are not being created, so what's going on here? Well, we're passing the classes directly to Google App Engine, and Google App Engine is creating the instances, and it's also creating the get method, which is an instance method. The main point of this example is to show you how composition and inheritance can work together in an external library that we create code to work with. What Google has us do when we want to build a website is define classes for each one of our pages and then just pass those classes to App Engine. So we're creating small cogs to work within the larger machine of Google App Engine code. And again, this is an example of composition and how it can work with inheritance. So in this lesson, we looked at a simple example and then a more complicated real-world example of class composition as an alternative to inheritance. Both of these paradigms allow us to work within a larger world of a software development team or with libraries designed externally. Coming up, we'll see if you can build your own class system using both of these approaches. For our second assignment, we're going to create a very simple hierarchy of classes that write to text files. One of the classes will write to a delimited file, and one to a log file. I've completed the assignment, named it assignment2.py, and then I'm importing that module, specifically the 2 classes that I wrote, log file and delim file. Log file takes a file name as an argument. Delim file takes a file name and a delimiter. The idea is that log file is going to write a log message to the file, and delim file will write a list of values separated by a delimiter. So it would be good for writing a CSV file. And down here, you can see I've run the program, and then I'm printing out the log.txt and the text.csv. As you can see, the date and the time are printed just before the log message. Again, this would be useful if you'd like to log any kind of message to a log file while your Python program was executing. Many times we want to do this when we're running our code and we want to see when certain statements were executed. We might want to see when we went in and out of functions, or we might want to mark the time before and after a database call to see how long it took. The delim file class will write a CSV-like output, and that's what's happening here. We've passed it lists, and it writes them to the text file. Now, the point of this assignment is to create a hierarchical class system. Log file and delim file are 2 separate classes, but they're both intended to inherit from another class. Your class structure would look something like this. A parent class, write file, would handle common functionality for log file and delim file. Log file and delim file are expected to inherit from write file, but the challenge will be to do it in as few lines as possible and make use of inheritance for this purpose. For example, since log file and delim file both write to a file at some point, you should probably put the file writing in the parent class and let log file and delim file call a parent class method to get that to happen. Don't find yourself writing the same thing twice. See if you can make it all happen without any repetition. I'll let you know my basic solution, where I wasn't trying too hard to be short, came in at about 25 lines, not including blank lines, and not including the calling code shown here, just the library code. See if you can beat that number, but make use of inheritance to enhance the brevity of your solution. Of course, you'll want to make sure that the write method is implemented in delim file and log file, And you'll probably want to make it an abstract method in the parent class, write file. For the log file date, we'll use the datetime module. Here's code for creating the date timestamp shown in the output. I'll just run it right here. You can just use this code verbatim to produce the date timestamp. One other thing to mention about this assignment is there's a little extra credit that's optional. Notice that I've put a comma in the value of one of the elements that I'm writing to the CSV file. Now, of course, a CSV formatter will be using commas to delimit the values on a given line. The way the CSV spec handles that is by putting quotes around any given value that have the delimiter in it. If I run this code, and then we take a look at the CSV file, you'll see that quotes have been placed around the element. This wouldn't be true of just the second element, obviously, because it's not happening in the next line. Your extra credit solution would look for the delimiter inside the value, and if it finds it, would put quotes around the entire value. It's very simple, but it's actually quite powerful when you consider that you can be building CSV files that could be opened in Excel by anyone. Here's my solution to assignment 2. As before, I'd like to emphasize that this is my solution, not necessarily the best solution. The length itself doesn't necessarily imply superiority. I know I challenged you to make it as short as possible, which is an important exercise, and I especially wanted you to eliminate duplicate code. But shorter doesn't always mean better. I've had students who have written incredibly short solutions that were equally difficult to read. The best solution is usually an intelligent mix of clarity of purpose, readability, and brevity. As long as you're evaluating your own work by this criteria, you should be okay. And the right mix of these qualities will depend on your own personal approach. In particular, we always want to ask whether something that we've written can be made shorter while not sacrificing clarity. And since we're working in an inheritance hierarchy, we want to take care to put all general functionality in the parent class and specific behavior in each child class. So as you can see, I've identified the functionality that both classes would need, setting the file name in the object in init, and writing a line to the file in a method called writeLine, which opens the file, writes the text to the file, and closes the file. But duplicating any of this code in the subclasses would be inefficient. If a change were desired, you'd have to change it in more than one place. If you decided to write to a database instead of a file, you'd need to change the duplicate code as well. Now, a log file object doesn't need to initialize more than this. It's simply going to write to the file using the name stored in the object. It can use the parent class in it. We simply don't put an init in log file. And when we create a new log file object, Python will eventually look in the parent class and call init there, moments after checking the log file class. But delim file does have another initialization step, and that is the setting of the delimiter, which we're doing here. However, it also needs to set its file name as well, and that's why we're calling the parent class constructor. Now, I realize that saying self.filename equals filename isn't a lot of code, so it isn't a lot of overhead to repeat this code in the init to delim file and avoid having to remember the syntax for calling the superclass constructor. And in fact, there is a school of thought that says that small amounts of code can be repeated if it's more convenient to do so. The reason this assignment challenges you to avoid duplicate code is because this is just a model of much more complex programs that would have far more complex initialization routines. The exhortation here is for you to always be on the lookout for duplicate code and use inheritance wherever you can and wherever it's practical to avoid duplication, which makes your code tighter and more maintainable. So writeLine is the common method that delim file and log file can use to write to the file, and they're both doing so down in their respective write methods. And of course, it isn't an accident that we named both of the methods write. This polymorphic behavior means that any class inheriting from write file could be understood to implement the write method and thus have it be available. In delim file, we're simply taking the list, joining it on the delimiter to produce the line that we want to write up in the file. And in log file, we're creating the date using datetime_now, then formatting it using the stirftime method and passing it as a string to datestir, which we're then writing in writeLine. First the date, and then the line of text that was passed to write. By the way, if the syntax up here looks funny, it's only because we're taking the delimiter and calling join on it. The delimiter is a string It would normally be a comma, but whatever was sent up to the constructor. So we're saying string.join and then passing it a list, which is the standard syntax for join. So overall, setting up an inheritance hierarchy, having two classes that implement the same write method, and creating a conceptual relationship where delim file and log file do similar things even though they do very different things, is a simple example of how we can create an inheritance hierarchy. The inheritance hierarchies that you'll find in the professional setting will obviously be far more complicated, but this is the basic concept. One thing I forgot to mention, set up as polymorphic, and it's the same name in each of these classes. We've set this up as an abstract method because we want delim file and log file to implement it. Now your code may look different. It doesn't mean it's wrong. The code that you write needs first off to do the job. Secondly, to try to follow some of the qualities that we look for when we're evaluating code quality. Clarity, maintainability, which means minimal repetitions, consistency, brevity. These are the most important things to think about, particularly at this level. Later on, we'll get to higher levels where we'll think about time efficiency and memory efficiency. We'll do the extra credit solution next. This solution takes the composition approach to solving the same problem. Our program is expected to produce write file objects that are formatted using another class that's passed in as an argument. And then the concept is that write file will instantiate the class that was passed to it, producing a new write file object that knows how to write CSV or log file messages. So the write file class takes a file name and a writer. It goes ahead and opens the file and stores the file handle. You didn't have to do this, I just chose to do it this time. So it opens the file and keeps it open. Our prior solution would open and close the file every time there was a write. There's some argument for that in that it doesn't keep the file open indefinitely, but I just chose the other approach. Since we're passing a class name to the write file class in the constructor, and that's getting assigned to writer, here we're actually constructing an instance of that formatting class. So we're getting back a formatter instance. So now we have the open file handle and the formatter instance. So when write is called, we simply take the formatter and call format on it with the text that was sent up to write, and then we're able to just write that to the file handle. Again, I could have opened and closed the file and write, and maybe I should have done that, but I just thought it was more convenient to work this way. And then I created a close method because, as you can see down here, we close each object. That means we're closing the file that's stored there. Now let's look at each of the formatter classes. The basic contract is going to be that it implement a format method because write is expecting it. As you can see, this is really very similar to the example we saw in composition. Format for a CSV writer takes a list, and then I'm doing the little extra work of looking through the list and seeing if the delimiter is in the element. This was the extra credit that I talked about right at the very end, putting quotes around any element that has the delimiter in its value. If you didn't do this, you could just take the list and join it to the delimiter as we did in the basic assignment solution. Down in log formatter, again with format, we're taking the line, creating the date time as we did in the previous solution, formatting it as a single line, and then returning it. Both cases we're returning the line, we're not actually writing it to the file, because we're expecting that write is going to call format, receive back the formatted line, and then write it. You want to apply some of those same concepts that I mentioned in the last video to this one to see if your solution is better or worse than mine. If you're thinking a lot about time efficiency or memory efficiency, you have to ask why you've chosen Python. I'm not saying that Python developers don't often think about that. They sometimes do. It really depends on the application of Python in question. I've worked in Python programming for several years, and I've never really had to think too much about time or memory. And that's just because the type of work we were doing didn't overtax the resources that we had. It is something to keep in mind, but when we're working in Python, we do want to think of clarity first. I hope your solution looks good, and if not, do as much of a one-to-one comparison between this solution and your solution, and ask yourself where you might have optimized your own code. This section covers some of the more advanced features of Python. We're going to look into a few of the internals that provide some pretty powerful tools. We're also going to get a taste for some of the deeper internals of Python that were introduced with new style classes, in which Python's object model got a pretty exhaustive overhaul. What's wonderful about Python is that behind its elegance are some pretty interesting internals. You're going to be richly rewarded learning about Python and about programming languages in general. Python offers rich resources and discussion about its internals, all available online. At the highest level, you can even get involved in the language as it evolves. In this lesson, we're going to look at how Python allows us to take advantage of its operators in our own classes. Python is largely just objects and method calls on objects, and this is going on even when it's hidden by some convenient syntax. Let's take the add operator, represented by the plus sign. As you know, it can be used to concatenate two strings. But as I intimated earlier, it can be reduced to a method call. In fact, Python reads the plus sign as actually meaning a method call on the L value, or left-hand object. That's this one, the L value, with the R value, or right-hand object, as the argument to the method. You may ask whether the same method exists for other object types that can be used with the plus operator, such as integers or lists. So when Python sees the plus sign, it actually converts this text here to this text just by converting the syntax. That's why we call the operator syntactic sugar. In other words, it doesn't have an intrinsic meaning other than it actually resolves to some other call. So then you may ask whether the same method exists for other object types that can be used with the plus operator, such as integers or lists. Why don't we find out? And sure enough, the integer type has an add method too. Once again, as I've explained, the double underscores on either side of an attribute mean that it's known as a magic attribute, and that means that it's usually called implicitly and not directly by us, although clearly it's possible to do it. What about lists? As you may know, they can be used with the plus operator as well. And sure enough, so this should indicate pretty clearly that Python just converts the plus sign to the add method call. So what does that mean for us? Well, we've been designing classes. So what if we were to implement the add magic method in our own classes? Could we make use of the operator too? Let's find out. So this class, SumList, has a constructor that takes a list as an argument. And as you can see, we're assigning it to an attribute in the object. Let's add an add magic method that works with two SumList objects. We have what seems to be a pretty involved class, but it's doing something that's relatively simple. The idea of SumList is that you could take two SumList objects, add them together, and their list elements will be added. 1, 2, 3, 4, 5 plus 100, 200, 300, 400, 500 would give us 101, 202, 303, 404, etc. As you can see, it's broadcasting a summing of the elements across the length of each list. This broadcasting behavior is similar to that found in data analysis packages like pandas and NumPy, which can take matrices of values and perform operations across rows and columns, and they call that broadcasting. Now, if you're interested in how it's working, you can take a look at this line, but probably clearer would be these 4 lines, which do the very same thing as that one line. Check out this code and see what you think. It's basically just doing what I said, taking the first 2 elements from the 2 lists and adding them together, second 2 elements, third 2 elements, etc., summing them in a broadcast sort of fashion and creating a new list with the values that we want, and then returning a SumList object with the new list. Now we're doing this under the add method, which means that we can take advantage of the plus operator. And so we're taking 2 SumList objects and causing them to be placed into the add call, that is cc.add object, which would look like this. And what we're getting back is a new SumList object. And then we're printing the SumList object to see what we've got. Let's take a look. So there it is. Now what about printing the object? That's actually where this other method comes in, the repr method, which is called implicitly when we do certain operations on the object. What we're doing when we print an object is we're actually asking the object to give us a string representation of itself. Now, string representation of an object can take many different forms, and it really depends on the class design what an object wants to say when you print it. In this case, we don't want it to say, I'm a SumList object, which would be the default. Instead, what we want to do is say, I'm this list, the same way a list object itself does when you print it. So the repr method which is obviously an instance method, is simply taking the string function and placing the internal list, that is the attribute myList, which is the list that SumList is holding, and rendering it as a string. And so that's why we see the output here. Now it's pretty interesting because I didn't have to do a lot to do some pretty interesting functionality. But best of all, I'm able to make use of an interface that everyone's familiar with, the plus sign. And when the user of the class asks how to use my class, I can just say, look, SumList works with the plus sign. If you add two SumList objects together, it'll broadcast the sum across the elements. I wouldn't have to make the user use a special method for that. I'm also taking advantage of the fact that when they want to print the object, they'll see something that they might expect. So it's very powerful functionality, and part of the power comes from the ability to communicate very easily what the object is all about. In fact, most of the Python syntax you see operating on objects is actually routed through these magic methods. In strings, we can see some very familiar operations. For example, the in operator, which resolves to a method called contains, the equality operator, which resolves to the EQ method call, a subscript, which resolves to getItem, or a slice, which resolves to getSlice. Len, we talked about earlier, as we just saw, print will call the repr method, although it may also call the stir method if it's available. So many other operations are handled by these internal magic methods, giving us the opportunity to make our custom-designed object's behavior work like Python built-in structures. You can easily find documentation on all the magic methods available to you. Rafe Kettler's guide is clear and concise, and you can see the URL for a page in which he describes them at the bottom here. So in this lesson, we learned about some of Python's magic methods and how they can enrich our class design by giving us access to Python's built-in syntax features. In this lesson, we'll learn about inheriting from built-ins, which means we can inherit from any of Python's built-in objects and take advantage of all of the functionality to be found there. This can give our own classes abilities that every developer is familiar with. Like our ability to make use of core syntax, we can leverage Python's core objects in interesting ways. Remember that inheritance confers attribute access. The instance of a child class can also access the attributes defined in the parent class. And this means that any methods defined in a parent class are also available to the child instance. We can also inherit from our old friends the built-in classes, like list, dictionary, tuple, and make use of their functionality in our classes. Here's a really simple example in which we're just inheriting from dict, the dictionary type, and we're not doing anything else with our class. So it's one of our objects. It's a myDict instance that gets constructed, but we can use it exactly the way we would a dictionary, because it's simply inheriting everything that the dictionary does. So in this example, we're inheriting from dict as we did before, but we're re-implementing one of its methods, setItem. SetItem is the method that's invoked when we set a key and a value in the dictionary, the way we're doing here. And of course, it's a magic method, which means it's called implicitly. And then just to demonstrate what's going on, we've got a print statement here, and then we're doing the real setItem, where we really set the key and the value in the dictionary. Now, what do you make of this? We're actually calling the parent class setItem. Why don't we just go ahead and set it right in the object the way we would expect we could? Well, let's try it and find out. We're taking the object right here, dd. It's a myDict object that inherits from dictionary. So we should just be able to set the key and the value right in the object, correct? All right, let's try it. Runtime error, maximum recursion depth exceeded while calling a Python object. Recursion refers to a function that calls itself. We're getting the same call over and over and over again, and when we see the stack trace from the exception, we're seeing all of those calls printed back. So what's going on? Well, when we set the key and the value in the dictionary, Python automatically calls setItem. So it calls the same method that we were just in. And then, of course, prints the same thing, sets the key and the value, calls setItem. This is what they mean by recursion depth. And by depth, they just mean that this function called itself, then called itself, then called itself, as if it was getting deeper and deeper and deeper into the calls. Eventually, Python just says, you can't do this forever. I have a limit. And that limit was known as the maximum recursion depth. This is why you'll need to do this in your assignment as well. We call the parent class setItem, because this will just do the normal thing. We pass our object as the object to be worked on, and then the key and the value. Now we can run this just to see that it works, and it does. So you can see that setItem here, now that we've redefined it, is a hook into some other functionality, and we can do whatever we want here before setting the key and the value. We could validate the key and the value, for example. Maybe we want to create a dictionary that only allows certain keys, or maybe we want to create a dictionary that only allows certain types of values, like this dictionary can only hold integers and its values. This gives us a great deal of power because our myDict object behaves like a dictionary object in every respect, except for the places that we decide we'd like it to behave differently. Now, this is a slightly more complex example. Something very specific is going on, and it's a strange outcome. GetItem and setItem are magic methods that are invoked when we use the list's index. And as you can see, we're inheriting from list. So my list is going to act like a list object in every respect, except when getItem and setItem are called. Now you can probably infer that these methods are similar to the ones with the dictionary. And as I mentioned, they're going to be called when we use the index. But setItem is also going to be called when we do things like append. Append simply determines the new index and then does a setItem on the list to add the new element. But what's going on here with the index? Well, in both cases, getItem or setItem, we're discarding the idea of a zero. If you try to use a zero index, you'll get an index error. And if you use an index that's greater than zero, the method reduces the index by 1 and then calls getItem with the new index. So what's really going on here? Well, why don't we run it and find out? We set a 3-element list in myList. Presumably the init is getting called in the parent class init, that is the built-in list. We're printing x, so we're seeing the 3 elements. We're appending an element, and then we're asking for index 1 and index 4. But take a look. We're getting A and spam. That's the first element and the last element. But as we all know, lists are indexed starting at 0. So what we have here is a list that has an indexing starting at 1. In fact, it's making up for the confusion that we've all had when we first learned about list indexing. This myList starts its index at 1. So now we have to relearn it. I've added some comments just to clarify things a little bit. Basically, we've created something that's really powerful, and yet it's relatively simple. Because we've inherited from list, we're able to make use of a lot of methods that are getting called without us even realizing it. The append method is getting called in the parent class. So is the repr method when we print our list. And of course, the init method, as we mentioned before. But when we do things like getItem, it's going through this special process. In this lesson, we learned about inheriting from Python's built-in objects and how we can use its magic methods to alter its behavior while retaining its other functionality. The elegance of Python's object model lends an overall elegance and power to the language, and we can make it work for us. Best of all, we can communicate the use of these objects extremely easily to our fellow developers. Just tell them it acts like a list, but a little differently. We don't need to learn any new method names or a new interface, an extremely powerful feature of this language. In this lesson, we'll discuss ways to indicate and in some ways to enforce the kind of privacy afforded by encapsulation and the setting of attributes. You'll remember that when we discussed attribute setting, we showed you that it was possible to set any attribute at any time in any object or class, and that it just works. Remember also that when we talked about this, we called it breaking encapsulation, meaning that setting attributes arbitrarily in the object doesn't force the user through a process that we control. We do want to make sure that mistakes aren't made when people are using our classes. Our solution to this problem was to employ a classic getter and setter paradigm for attribute access. We'd create getter and setter methods and then ask the user to make use of them when they want to change attributes. And again, this would depend on the user's cooperation. Some of you, particularly if you've been exposed to another language that employs more strictures in this area, such as Java or C++, might have been dissatisfied with this, because we do want to have a sense that our classes will be used properly. But it should definitely be clarified that as a scripting language, Python, by design and intention, does not enforce privacy. And it's considered decidedly unPythonic for a code designer to try to do so. Instead, we rely on documentation and the user's cooperation in the proper use of library code, like modules and classes. Python does have a way to take some control when the user accesses a particular attribute. In other words, to promote encapsulation during attribute access. And this is done with the property function and its corresponding decorator. But I think it's fair to say that this feature isn't about control. It's more about convenience. It lets us perform functionality when an attribute is accessed, and it lets the user of our class use simple attribute access rather than having to call a method. So here we have our regular getter-setter class example, but we're using a new decorator called property instead of getter and setter methods. Look closely. We have three methods with the same name, var. This would cause some conflicts, obviously, if we weren't using the property decorator and its setter and deleter decorators. So the first var is decorated with property, the second with var.setter, and you can see that we're using the same name in the decorator that we are in the method. And then we have var deleter, again, def var. Now you might also notice that the var being used in all these places is the same as the name of the attribute. In order to enable attribute encapsulation using the property decorator, we can choose any name we like, but we're going to employ it in all of the three method names and in some of the decorators as well. I'll just run it to show you that it's working. So you can see that when we set the attribute var with 1000, it calls the method decorated with var.setter, and we see setting the var attribute. When we read the value from the var attribute, it goes up to the method decorated with property. And then finally, when we delete the attribute, which would normally remove it from the instance, it calls the method decorated with deleter. Now note that the actual attribute name that's being used internally is not var, it's attrval. So there's an underlying name for the attribute, but its outward-facing name is what we tell the user to use, var. By the way, if it was the same name as the actual attribute name, we would have a problem if the script set the attribute. Then Python called the decorated function, the function tried to set the attribute, Python called the decorated function. You'll see a maximum recursion depth error just like we saw last time. When we read the attribute, Python calls the var method we decorated with property. So now the user is freed from having to use getter and setter methods to read and write attribute values. And we can still employ encapsulation to enforce this important technique. Now, this doesn't keep the user from setting and getting values for attributes for which we haven't defined such methods. But again, we don't want to feel the need to have too much control. In fact, there's a feature called slots, which enables this type of control, but it isn't even designed for such control. It's really designed to help limit the amount of memory that's being created when you create numerous instances. It's said that you should try to avoid using properties for computationally expensive operations, basically because they look cheap. And by cheap, we just mean that when you say object.attribute equals, it just seems like you're setting a very small amount of memory in the object. But if you're calling a method that does something that's expensive, like allocates a great deal of memory, makes some sort of expensive database connection, etc., it might be misleading to the user if you allow all this to happen through simple attribute assignment. So in this lesson, we learned about the properties decorator, which gives us a very handy facility for controlling attribute access. This control allows us to encapsulate the values of attributes so that the data held by an instance can be controlled and its integrity be maintained, in the same way that we did with the standard getter and setter methods that we discussed much earlier. In this lesson, we're going to look at the names we use for variables, especially private variables, and talk about the conventions that are used by Python programmers worldwide. We'll see that although variables can be designated as private, there's no real privacy in Python, and this is by design. Now, like other languages, Python has a set of naming and style conventions that it promotes, although it doesn't enforce them. There's a style guide co-written by Guido van Rossum, the author of Python, that describes the best coding practices, including the use of names, and it's called PEP 8. PEP 8 is actually another resource that you can use to gain greater insight into the language. It discusses some philosophy behind some of these conventions, but best of all, it specifies a style that's considered to be professional style. So if you're interested in producing code that looks professional, you can't do any better than to follow the conventions that are shown here. There are also some tips for good coding practices as well. PEP, by the way, stands for Python Enhancement Proposal, and it's a series of documents that are shared among the Python community to discuss proposed changes to the language. For example, it's recommended that all function and method variable names be all lowercase, with underscores separating words, and that classes should be capitalized, because it's considered more readable, and it's such a strong convention that most developers follow it. You may feel that your variables should be named according to your own preferences. For instance, camel case, which is what we use for class names. Maybe you want to use that convention everywhere in all your variables. Even though you're allowed to divert from the convention, you shouldn't. Because if you do, your code will be arguably less readable. But more importantly, other developers will see your work as amateurish. Potential employers looking at your code samples will think that you're not aware of the conventions. And again, let me say that although we tend to conform to convention, and that makes us seem conformist, good developers know that there are other ways to express creativity through algorithmic design and interface design. Well-designed code can really unlock your creativity because clarity and following convention can help you write better code. So in Python, especially when we're working within modules and classes, we designate some variables or attributes as private. And private simply means that they're not intended to be used by users of your code. Instead, they're intended to be used internally. So here's the naming conventions that we follow. Public attributes or variables should be named with regular lowercase variable names with words separated by underscores in the name. Private attributes or variables should be designated with names that begin with a single leading underscore. This is for variables that are not intended for users of your code to access. They're being used internally. I should probably mention that the import statement from module name import star doesn't import these names, but I don't emphasize it because I don't think import star is a particularly good practice. For private attributes in a class that you don't want to be included in a subclass, you can write your variable names preceded by a double underscore. I'm going to explain exactly what happens when you do that, but like the private attributes with the single leading underscore, it's a designation. Finally, for magic attributes, that's attributes that are internal to Python, you'll see double underscores on either side of the variable name. But generally speaking, you should not invent your own variables using this convention. These magic methods have been defined by Python, things like init or add or len, attributes that we've seen, and they're internal. They're not created by users like us. So in this example, which also demonstrates the use of the property decorator, we've made sure that the internal attribute @val, which you see here, has been preceded by an underscore. This designates it as internal use only. The attribute var, by contrast, is not intended to be private. In fact, it's part of the public interface for this object, so it has a normal name. That's what we're seeing down here. Also, to illustrate this, we've added an instance counterclass variable, which is also intended to be used publicly. Finally, we have what we're calling mangled name, and I'll explain why in a second. This is one of those specially designated variables that's not intended to be subclassed. If we should create a child class of getSet, mangled name is designed not to be used there. We can run this to see how it works. As you can see, we're setting the var attribute. That's something that happens when we set a value to the attribute var. It's happening up here. Notice, though, that we're able to print the value of the private attribute. Now, again, privacy isn't enforced. It's not Python's way to do this. The single leading underscore is just a designation, but it doesn't mean that we can't access the attribute just like any other. It's just understood that a user of our code knows the convention and won't go around using these attributes. Finally, we have mangled name, and as you can see, it's called double underscore mangled name. Now, if we were to try to access that through the instance, normally we should be able to. But we get an error, not defined. And that's because the name has been mangled, and mangled is a term they use to mean changed. Outside of the class, it's been mangled to become this, which is single leading underscore, name of class, and then the double leading underscore and the name of the variable. So that will work. But in this particular case, you'd have to really go out of your way to access this variable. It's just one additional little hurdle if you want to get around the restriction. And it should be clear to any user of the code that this really is not intended to be used even by a subclass of this class. Even though Python has certain conventions to designate some variables and attributes as private, it has very few strictures to keep you from using private variables in any way you wish. In other words, there's no easy and built-in way to designate a variable or attribute as completely unavailable to another part of the program. As an interpreted scripting language, Python adheres to a different principle, the idea that users of your code will read the documentation and cooperate with its intentions. In this lesson, we'll look at a built-in feature of Python that allows your object to do cleanup or closing routines automatically. It's called with. The with statement is most commonly used with Python's file object. Here's a recommended way to open your files. With open file name as fh is a new usage, and we're using the with block here. And then notice that we're indenting. Then we go ahead and use the file handle to loop through the file in a very standard way. Let's just compare this to the code that we might use before with. fh equals open for line and fh, print line, fh closed. So what's missing from the first example that you see here in the second example? It's the call to close. Closing a file handle is considered very good practice. Although files are not locked when you open them, and they get closed when your Python script exits, it's usually considered good practice to close your files as soon as possible, just because the operating system is keeping open a small amount of data when it keeps your file open. And also because there may be text sitting in the buffer that won't get written to the file until the file gets closed. But closing the file handle can be a bit of a pain, and it can be a bit of a pain if you're short-circuiting out of a function. And there are other situations too where closing the file handle isn't terribly convenient. So the with context adds this wonderful new facility for doing cleanup routines on an object once we leave the block. At this point of the print statement, file name, which was opened up here in the with block, has been closed by the time we reach this print statement. And that's because once we leave the block, Python executes a bit of code that's been added to the file handle class code. And what we're going to do in this lesson is show how we can use with in our own objects. In this example, we'll show a basic usage of with our usual favorite, a class that really doesn't do much of anything. As you can see, we're creating a myClass object using with. And remember that with will say with operation that produces object as label that will hold the object. So it's as if we had said cc equals myClass, but instead we're saying with myClass as cc. It's just the syntax that they use for with. Okay, so once we've created this myClass object, we then call sayHi on the object. And then once we're out of the with block, do a print statement. Now the reason we have this print statement is that we have other print statements that indicate what's going on. Let's see what's going on inside the class. We have two special new magic methods called enter and exit, along with our sayHi method. Let's execute it and see what happens. We've entered with, that happened here. We called sayHi, then we are leaving with, and then after the with block. So we have entered with. Enter, the special magic method, is executed at the beginning of the with block. So as soon as we said with myClass as cc, enter was called. And notice that this is an instance method, so it's taking the instance, and we could do something with the instance if we wished. Then we call sayHi, and that's why we see hi instance and then the instance ID. Finally, we leave the with block, and we see we are leaving with, which means that exit got called. Enter gets called at the beginning of the block, and exit gets called automatically at the end of the block. So why would this be useful? With could be useful for any class that needs to do cleanup when it's done its job, and it may not want to rely on the user to explicitly invoke that routine. For example, let's say that your instance allocates a network resource, and it needs to close its network connection when everything's done. Or perhaps your class does a data-intensive calculation, which allocates a great deal of memory, and we'd like to see that memory deallocated at the end when we're done with the instance. Or perhaps our object uses a database connection, and since they're in pretty short supply, we'd like to close the connections at the end. Now, all of this can be done in our class through a regular method call. With is simply an additional feature that makes it easy to do cleanup. And sometimes it's really useful in situations where it's just awkward to issue that last closed method call. And a good example would be the one I gave before. When you're returning from a function or a method prematurely before the actual end of the method block, it's not always convenient to issue a close statement or call some sort of cleanup routine when you're done with the object. With just takes care of it for us. With can also be used to catch an exception that might occur within the block. And I've just added some code to illustrate this to the exit block. As you might have noticed from our previous example, any exit definition needs to include not only the instance, but 3 other arguments. And these 3 arguments are values that would be set if an exception occurred. Now we're discussing exceptions elsewhere in this course, but for now I'll tell you that the exception has a type, it may have a value, and it has a traceback, and we'll see what all those are in just a second. Let's add some code here that will create an error. All I've added here is this additional line, 5 divided by 0. Machines hate to be told to divide by 0. And let's run it and see what happens. Okay, there you go. The error type is 0 division error. The value is the string, integer division or modulo by 0, and this is the traceback. If somewhere in your with block an exception occurs, you can use exit to capture the errors. So in this lesson, we learned about the with block, which is known as a context manager because it performs within the context of having entered the with block. We can incorporate this feature into our own classes if we're interested in performing a cleanup routine, regardless of how the user leaves the block. In this brief lesson, we're going to discuss new style classes and talk about the differences between new and classic classes. New style classes were added in Python 2.2. Old style classes are retained for backwards compatibility. In Python 3, they made a break with the past and all classes are new style. You may be dealing with old style classes if you have some legacy code, but all your new code should definitely work with new style classes. Here I've created an old style and a new style class. Can you see the difference? All new style classes inherit eventually from object. And this is why I've been hammering home in all of my examples that we place object in the parentheses of any class that we create. All of your new classes that you create now should be new style. Let's start by looking at the most visible difference. If we take an instance of an old style class and an instance of a new style class, one inherits from object and the other doesn't. And then we print the type of each of these objects. Let's see what we get. I'm going to comment this out so that our output is clear. Type instance for the old style. Type main new class for the new style. Main, I may have mentioned earlier, is the module that we're in. It's not so important. What's important is that we can identify this instance as being from a new style class. However, the old style class is of type instance, which isn't really terribly helpful. I'll let you know that if you're working with an old style class and you'd like to know its type, you can get it from the class attribute, which will tell you. In old style classes, the concepts of class and type were not related, and in new style classes, they're directly related. So one of the motivations of new style classes was to unify the idea of class with type. As I mentioned, new style classes inherit from object. One of the enormous differences with new style classes is that they can be constructed with default attributes and thus default behaviors from meta-class constructors. Just like a class can create an instance, a meta-class can create a class. And this allows us to create classes with special behaviors. A singleton class is one that allows only one instance to be created. As one of the benefits of implementing this full meta model in Python is the allowance of the subclassing of built-ins, like we're doing elsewhere in this course. Another important feature that we haven't discussed because we don't want it to be misused is the use of slots to define instance attributes. Slots will allow you to define which attributes are possible to be added to an instance and which aren't. Its main purpose is to save on memory. Another enhancement is the use of the method resolution order called C3, and I went over this when we discussed inheritance. Although most inheritance trees result in a depth-first search, the special added rule was that if we have any inheritance patterns that result in a class appearing more than once in the inheritance tree, its earlier appearances in the inheritance order are removed. New style classes also support descriptors, which are sort of like constructors for the getting and setting of an object's attributes. A descriptor can, for example, allow an object to have read-only attributes. They are central to the new way of looking at objects in new style classes. And as I mentioned, new style classes are the only type of class that are available in Python 3. The only reason they haven't been removed in Python 2 is for backward compatibility reasons. I suggest that if you're really dedicated to learning Python very deeply, to search online on the subject of metaclasses and descriptors, as well as new style classes. So I encourage you to read further. In this assignment, we're going to leverage the power and convenience of a dictionary to stand behind a configuration file, which is simply a file of key-value pairs. Our purpose is going to be to create our own class that inherits from dictionary, so our instances will behave like dictionaries. But when we set and get values in the dictionary, what we'll really be doing is setting and getting values from a text file that holds configuration values. The benefit here is that by using the dictionary, we're able to use an interface that's very simple and straightforward, but that by using it, we'll be able to store keys and values for use elsewhere in the code. Here's our simple configuration file. A file like this one is used quite often by developers to hold values that don't belong in the Python script itself. Values like SQL queries, email addresses, and things like that should be stored outside of the script because they're basically content. Content changes should not require that we go into our code to change them. The structure of a configuration file can take many forms, and one of them is a simple key equals value syntax with one key value pair per line. So you can see we're saying SQL query equals, and then the query, email to equals, and we've got these keys and values. Now the purpose of our class is to be able to read this file and create a dictionary out of those values. And then when we write to the dictionary, we're actually writing to the file. So the interface will be a dictionary. What's brilliant about using a built-in structure like this, as I mentioned, is that the interface is familiar to every Python developer. So we don't need to give them special instructions to use it. Just tell them that the dictionary is tied to a file, and if you make changes to the dictionary, it'll change the file. And the developer will never have to ask for those instructions again because every developer knows how to use a dictionary. From a design perspective, using a dictionary is relatively easy. Just inherit from dict, and then override or re-implement the setItem method, which will write to the file. And we have examples of this in some of our previous lessons, in which we use setItem to re-implement the behavior of a dictionary and of a list as well. So the instance should be initialized by reading the file specified in the constructor, loading all of the file's key value pairs into the dictionary, and then returning the object. Then when a change is made to the dictionary, Python will call setItem on the instance. You will define setItem to set the key and the value in the dictionary, open the configuration file for writing, write the dictionary's key value pairs to the file, and then close the file. Again, if we ever set a key and a value in the dictionary, our class will write to config file. It'll take the dictionary's keys and values and rewrite them all to the file every time we set a key and a value in the dictionary. This way, the text file that holds the key value pairs is always up to date and always reflects what we have here in the dictionary. So here's a very, very brief model of what your code will look like at the very beginning. This class doThis inherits from a dictionary, so it's going to behave like a dictionary. And again, we have examples of this in our section on subclassing built-ins. As I mentioned before, if we create a new doThis object, we've got a dictionary on our hands. And if we use the key value syntax to establish a key and a value in the dictionary, it's going to call setItem, and it'll be passing this value as the key and this value as the value. This is actually a problem, and you want to be very careful. Obviously, what we're doing is trying to set the key and the value in the dictionary. If you do this, it will call setItem again. SetItem will want to set the key and the value. It will call setItem again, etc. So this will cause an endless recursive loop, which actually finally ends when Python decides that we've gone too far and it wants to stop us. So the thing to do in that case is to call the parent class setItem with self, key, and val as the arguments. And that will avoid the recursion that we've been talking about. So I've written a short program that can test your class once it's completed. You don't have to use it, but it can be helpful. This assumes you've created a class called config_dict. That would be the class that will satisfy the assignment. I've placed it inside a module called assignment3. Assignment3 is a module that holds config_dict, and that's the meaning of this import statement. Your alternative to this could be to just create the class and place it right in this file, in which case you won't have to import it. The purpose of this script is to allow you to either set a key and a value in the dictionary and the config file, or to read out what's in the dictionary and thus what's in the config file. Right now I believe I have nothing in the config file. And what I'm going to do is run the code and show you two ways that you can run this program. And the usages are shown here. You can run it with a key and a value, in which case it'll set it, or you can run it without a key or a value, in which case it'll just show you what's there. Set key 1 to the value value1, and it tells us writing data, key 1, value 1. I'll try it again. Other key and other value. And it's writing the data. So now if I do a cat of config file, and all I'm doing really is just showing the contents of config file. If you're in Unix, you can use the cat program. If you're in Windows, the name of the program is type, although you can also just open the file to see what's in it, and that's all I'm really doing here. You can see that it's set the key and the value as key equals value in the config file, and put one key and value pair per line, as we showed in the example file earlier. Now if I run the script without a key and a value, it'll show me what's in the file, because all it's doing is taking the object from our config_dict class and treating it like a dictionary, reading out the keys and the values. So that's it. You don't need this script, but this script could help you test your class while you're working. My solution is 15 lines, not including the calling code here, or any blank lines. Yours certainly can be longer. Don't be too obsessed about making it short. I'm only quoting my own program's length because I want to emphasize that what we're doing is relatively simple. And by the way, because this assignment is potentially involved, I've decided to include an optional supplementary lesson with hints and a breakdown of what you need to do to complete the assignment. It's optional, so feel free to work without it, in which case you wouldn't listen to the next video. But if you'd prefer a real breakdown, check it out. It's the lesson immediately following this one, and after that, we'll go over the solution. Also, don't forget that all assignments are restated in text in the working files. In this lesson, we're going to discuss in some detail the steps you'll need to take to complete assignment 3 in this course. The assignment is relatively simple, but it has a number of tools and features that you may or may not be familiar with. You can skip this video if you'd like to try to solve it on your own, or use these tips to get started. My purpose overall is to keep you from having to spend way too much time on the assignment if you're not familiar with some of the aspects. I should emphasize that I'm not going to show you the actual code you'll need, but I'm going to demonstrate some of the tools. So let's get started. The first tip is to inherit from dict, which is the point of the exercise, to make use of a dictionary's functionality. And again, some of the code I might show you may not compile, it may not run properly. That's only because I'm showing you snippets that can help. So you can see we're inheriting from dict. That means that any object that we create out of this class is going to act like a dict. Anything that we add to this class may change its behavior. Next, let's see what has to happen in the init constructor. The first thing we'll need to do is set the name of the file in the instance, since we're going to need it later. I would use a private attribute name for this, and as you know, a private attribute begins with a single underscore. The next thing we would do after setting the file name in the instance is to check to see if the file exists. Otherwise, we'll get a nasty error if it doesn't. So we can do this. Obviously, since OS path isFile returns true or false, we would use it in an if expression. Back in our init method, once we've checked to see if the file exists, if it is, we'll open it and read it line by line. And then for each line in the file, we'll strip the line and split on an equal sign. Now there is one thing I can mention about split. It's going to split on every equal sign that's in the value. If your value says this equals that, you'll have no problem splitting it. But what if your equal sign actually appears in the config value? It's possible. you'd want it to split on just the first equal sign. So you'd do something like this. There's a second argument you can add to split that will give the maximum number of splits. In this pseudo example, config val would be the value that you're going to split. The 1 as the second argument to split guarantees that if equal sign is in there, you'll get 2 values and not more. So in a value like this one, it would split on the equal sign and only split once, and then this would become the key and this would become the value. Because it could matter if you tried to apply this to a real-world situation, I wanted to let you know about it. So we've added a few more comments here to show what to do. At this point, now that we've split the line from the file and made it into a key and a value, the thing that we don't want to do is set it directly in the instance. If we use this standard dict setting approach, it will call the method that we will be overriding in our class here, that is setItem. Now we're not in setItem, but we'll be doing something else in setItem as well, which is write to the file. And since we're only just reading to the file, we're going to want to use the parent class version of setItem. So this is what we'll use to set the key and the value in the dictionary. Now let's implement the setItem method. As you know, this method gets called when you set a key and a value in the dictionary. For example, myDict key equals value. In other words, when we say something like this. So we want to do two things in this method. First, set the key and the value in the instance, and then write all the keys and values to the file. So if the file already exists, we're just going to wipe and reload all of the keys and the values from the dictionary. First, set the key and the value in the instance. To do that, we'll use the same call to dict that we did in the init method. That is dict.setItem, self, key, and value. And we'll be doing that down here. And then to write the file, we're going to have to open the file and then use the write method on the file handle, taking care to put the key and the value on the same line, separated by an equal sign. So having opened the file, we'll loop through this instance's key-value pairs, that is, in self, and then we'll write each key and value on a line joined by an equal sign. And it'll look something like this, using the format method with the 0 and 1 tokens to insert key and value. Now, I haven't explained everything, obviously. Some of this is basic knowledge that I would want you to know before taking this course. If you don't, you simply need to look some of these things up. For example, I never really talked about what stripping the line is about. I'm talking about calling rstrip on the line of text to remove any white space. I don't have specific code snippets for you to use because I want you to construct them yourself. I'm trying to offer some help without giving away the whole solution. As I mentioned, a written version of this assignment, as well as these hints, can be found in the working files. Here's my solution to assignment 3. Again, this isn't necessarily the best solution, although I think it's pretty clear and pretty brief. We need to be able to initialize the class by reading from the text file and storing the keys and values in the dictionary. And then we also need to implement a setItem method, which will be invoked when we set a key and a value in the dictionary in the object. So let's start with init. Our code is going to look something like this, passing the file to the constructor. And of course, that's why we're copying it up here. We then store it as an attribute in the instance. And we're using the single underscore in the beginning of the name to indicate that this name is private, not expected to be used out here. Next, we use OS path module to see if the file is actually a file that we can find on the operating system file path. So os.path.isFile, and then the name of the file, which we've already stored in the object, will return true if the file actually exists. If it doesn't, we're not actually reading it at all. We should probably have an error message at that point. We're talking about exceptions elsewhere in the course. So if the file does exist, we say with open file name as fh, using that with that we talk about elsewhere in the course as well. With the file being open, we say for line in file, strip the line. What we're really aiming at is the new line that appears at the end of every line of a file. And then we're splitting the line on an equal sign with an argument of 1. 1 here is what's called the max split. It limits split only on the first equal sign. The reason I'm doing this is just in case the value should have an equal sign. We wouldn't want split to produce 3 or 4 arguments, which would cause an error here, since we're trying only to capture 2 arguments. So with our key and our value, we're then calling dict.setItem. The reason we're using the parent class setItem is because if we use this class's setItem, it'll be calling the one that we've created. And actually, there's some extra behavior that we don't want at this point. While reading the file, we don't want it to be writing to the file. So that is our init, simply checking to see if the file exists, opening the file for reading, and then for each line in the file, splitting out the key and the value and setting it in our instance. Now, what happens when we want to actually add a key and a value to our dictionary? Here we're setting the string key to be associated with the value in the dictionary. Now, as you know, when we do this, Python wants to call setItem. And since we've implemented setItem, it goes straight to our version of setItem. Because of inheritance, if we hadn't implemented setItem, this operation would simply call the parent class setItem, the one that's built into the object dictionary. Having called setItem with a key and a value, and the instance, of course, we're now going to call setItem on the parent class in order to get it into our object. Again, if we simply use this syntax or called setItem on our own instance, it would create a recursive loop, and we'd have setItem calling setItem over and over again. So we call the parent class setItem in order to set it in the instance. Just because we're calling the parent class dict setItem doesn't mean we're actually setting it in some other dictionary. We've passed self as the argument, so the key and the value will definitely be set in our instance, even though the parent class method is doing the job. Then, of course, once we've set a key and a value in the dictionary, we're going to want to open up the file for writing and rewrite all of the keys and values from our dictionary into this file with open, file name, W for write as file handle. Now we loop through the items in our object, which is the key value pairs in the dictionary. And if you're not familiar with items, it loops through and returns two element tuples, the key and the value. And these are being assigned in turn to each key and value. We then take this key and value and add it to a new line that will become part of the file. That is key equals value. And we're using the format method of the string object to insert the key and value into 0 and 1 here in this string. Taking that resulting string and writing it to the file handle that we had opened for writing. So that's the solution. You'll want to compare the choices you made with the choices that I made, and then make a value judgment. One might be better than the other for one or more reasons. With short programs, your program should probably look pretty similar to this. As programs get longer, of course, you have more opportunities for creativity and optimization. And if you've made a shorter solution, that's great. Just make sure that it's readable, because readability really comes first. This short section is about exceptions, how we can trap them, raise them, and how to design our own exception classes. In this lesson, we'll introduce the exception error handling system, discuss how to trap exceptions when they occur, and how to raise them in our own code. If you're already familiar with trapping and raising exceptions, you can safely skip this video, although you may want to look at the next video in which we'll define our own exception classes. Every error Python encounters results in an exception, which is an error condition identified by a type. The one I just showed you was the zero division error, and there are other ones I'm sure you're quite familiar with. Here we've misspelled a variable name, so we get a name error. Here we've failed to close the quote on a string, so we get a syntax error. And I'm sure you're familiar with this one. Here we're asking for a key that doesn't exist, so we get a key error. And similarly, if we ask for an index that doesn't exist, we'll get an index error. Now let's talk about trapping these exceptions, because there are certain types of errors that shouldn't result in the end of everything. And as you know, standard behavior when an exception is encountered is to simply terminate execution of the program. We've established a 4-pair dictionary. We're using the raw input function to ask for a key, and then we're printing the key and hopefully the value based on the key from the dictionary. If we run it, we're asked for a key. We'll ask for B, and we'll get back 2. If we run it again, ask for a key and offer a bad key, we get a key error. Now this would be user error, the person running the code. Now, obviously, there are ways to avoid this problem by checking the dictionary ahead of time or by using the dict get method. And checking ahead of time is always an option, but it's usually considered better to risk the error and then handle the exception if it occurs than it is to do testing beforehand. So if we want to trap this exception, the first question is to ask what type of exception we're going to trap, because each exception has a type, and we want to be precise about what we're trapping. How do we determine the type? Well, the easiest way is just by causing the error and seeing what type of exception results. And as you can see, when we ask the dictionary for a key that doesn't exist, we get a key error exception. So here's how we can trap the key error exception: by placing the code that we believe will cause an exception to be raised inside a try block. And here's the particular place where we feel we're going to get the error, asking for a key that doesn't exist. The code to be tested is in the try block, and we follow the try block directly with an except block. The except statement is followed by the type of error that we're expecting. And again, we determined that type by causing the error and seeing what came up. After except, you can see we've got another block. And in this block, we put code that will execute if the error occurred. So in the cases where we don't create an error or an error does not occur, we see testing for error, which was part of the try block. The value for A is 1. That line executed successfully. And then program continues. So you can see the except block was entirely skipped. If we run it again and put in a key that does not exist, we get testing for error, trapped error. The key X does not exist, and program continues. So again, after testing for error, Python attempted to execute this statement, but this statement was the one that caused the error. So we jump down to except. If we put in a statement here that says everything is okay, and try running this code again with another bad key, you'll see it never does execute everything is okay. And the reason is that as soon as the error is trapped, execution goes directly to the except block. And of course, again, if an error does not occur, we don't enter the except block at all. Testing for error, value of A is 1, everything is okay, and then program continues. What's most significant about our trapping this exception is that the program does not terminate. It continues executing. And this means that we're handling the error and we're not allowing the program to just suddenly end outside of our control. If we wished it to terminate at that point, we could call sysexit. But we'd be doing that on our own terms. Or we could do other things as well, return from a function we were in, call another function. This is what we call exception handling or error handling, and it simply means that we take control of the program flow when an exception is raised. And by the way, you can also trap two exceptions in one statement by placing the exception types in a tuple. So here we're trapping an index error and a value error. The index error will occur if we attempt to read an argument from the command line that hasn't been passed. And we'll run this to see. Now we've actually created the error condition by not passing an argument. It allows us to accept arguments on the command line like this. You can see at this point, we both passed an argument that was read here, and then we were able to convert it into an integer. When we run the program with an argument that is not convertible to an integer, we get a value error. And thus again, the except block executes. So in this case, we're capturing both an index error and a value error, basically because if either thing went wrong, we want to do the same thing. Now, exceptions are an elegant mechanism for handling errors. To understand why it's so useful, consider the many calling contexts that inhabit our code, the code that we import, and the code that imports our code. Because oftentimes we're writing code that not only makes use of libraries that we didn't write, but we also may be writing code that may be imported by someone else's code. And of course, all our code is filled with function calls. If you consider this code, in which I'm calling main first, then main is calling some major func is calling some util func is creating a myClass instance and then calling do something on it. Do something is calling make error, and make error is dividing by 0 again. What we're seeing is a series of calling contexts. Every time we enter a function, we're said to enter a context. And when an error occurs, Python is aware of the context we're in, and it's also aware in all of the contexts that we've been in. So let me explain what we often see when an error is raised and we see what's called a stack trace. Entering main, entering some major func, entering some util func, do something, make error. These statements were all part of the code that we wrote. As you can see, every single function shows us entering or leaving the function. And then the error occurs in make error, divide by 0. This is our traceback. And what we're seeing here is referred to as a stack trace because it traces the stack of calls which led us to this point in the code. Calling, of course, refers to each of the function or method calls that occurred along the way. And it's called a stack because when we enter a function, we're entering a new context, but we haven't yet completed execution of the old context. Consider the nesting that's going on here. When we finally return back to main, we'll see leaving main. In other words, we'll finish executing the code. I could demonstrate this by removing the error and running the code again. This time we see entering, entering, and then leaving, leaving. And you can see that the leaving is in reverse order of the entering. And why is that? Because, of course, every time we return from a function, we go back to the old function. So main calls some major calls some util, and we go up and up. And then when we return, we're coming back. After some util function is done, calling do something, we see leaving some util func. It goes back to some major func, leaving some major func, etc. And again, that's why we're seeing this series of statements, both entering and then finally leaving. But when an error does occur, and we're in the middle of such a set of calls, we're in the middle of a stack. It's called a stack because of the way we've layered one call upon the other. We haven't left the functions that we entered, but we've entered a new context. And so that context is said to be laid on top of the old context. And that's why it's called a stack. So we call this a stack trace, and the reason they say traceback, most recent call last, is that they're going to show us the order in which the calls were made, and the last call will be the most recent one that was made. And that's when we get this exception. Now, what's particularly useful about exceptions and calling contexts is that the error can be trapped at any call, at any place along the call stack. We could place a try except right around the code where the error occurs up here. We could put it around the method call that led to this block. We could go further back around the call to the do something method. Put the try except around main. Let's try it. It didn't manifest in our output because we were able to trap it here. So let's get back to this idea of exceptions being elegant. If we can trap the error anywhere, this means that we can choose to handle an error or pass it on to another context. And as we mentioned before, oftentimes our program is not just standing alone. It's importing other code, and sometimes it's being imported by other code. In this course, we're learning how to create classes, and classes are often library code that we'll give to other developers to use, or we may even write them as library classes for ourselves to use. In either case, a very restrictive way to handle errors would be to exit from the function or method directly. This takes control away from the person using our code. It would be actually quite arrogant of us to assume that the error should be handled with a sudden exit. What we should do if an error occurs is allow the exception to pass to the calling context, where we have the option to handle the error, or we can let it go up to the previous calling context where we can handle it there, or we can allow it to bubble up as far as we'd like. If it bubbles all the way back up to the level of Python's execution, then the program will terminate and we'll see the error. There's control at any point along the call stack. The last thing we need to discuss is how to raise an exception ourselves. That is, how to place the program into an error condition. We might want to do this in our class or module if we decide that something is wrong even if Python doesn't think so. Or we may want to raise a different exception than Python would raise and say something more helpful. Let's take this code in which we are taking a list and joining it together on a delimiter. The problem is if the user passes a non-sequence, like an integer, we're going to get a type error exception. What's less than optimal about this is that the user may not be familiar enough with our code to identify that their input was the problem. In other words, if we run this code and we get type error, it may or may not be entirely clear to the user that the problem was that they passed 100 instead of a list. In larger programs, it becomes even harder to figure out what's going on if we're buried deep within a utility function and we get an error like a type error. So we'd like to try to rewrite this and raise the error ourselves with a more descriptive error message. So here we're trapping the error with except type error, but we're then re-raising type error with a message that's meaningful. We name the function that we're in, and we also describe what the problem is. An instance of the exception class becomes available to us at the time that we trap it if we follow the class name, comma, and a variable. That variable is an instance of this exception class, and it has two attributes that we can rely on. They're not always populated, but they often are. They are message and args. When we run this, you'll see that message is the message that Python is displaying, or that it would display if we didn't trap the error. And args is a tuple, which just contains the message as the first argument. But if there are other values that are necessary to the exception, they'll appear in this tuple under the attribute args. So in this lesson, we learned how to trap and also how to raise exceptions. We learned why Python's exception handling paradigm is elegant and powerful. There are more details to exceptions than what we're covering here, but these basics are what we need to start talking about creating our own custom exception classes. In this lesson, we're going to learn how to define our own exception types through the use of classes. We'll also take a look at Python's built-in exception types. In our own code, as we discussed, we may wish to raise an exception of a certain type. For example, if a user calls one of our functions that requires a date in a certain format, as this one does, in the format 4-digit year, 2-digit month, and 2-digit day, we can validate the format and raise a Python built-in exception if it's incorrect. This research test uses a regular expression to validate the date and make sure that it's in the format that we wish. If it isn't, we have the option of raising an exception, and in this case, a value error seems in order. So with the correct date, we get the message that we want, and with an incorrect date, we've had Python raise a value error for us. We've also placed a message into the argument value error. This becomes part of the message attribute, as we mentioned last lesson, and it's also, of course, displayed in the output. So when raising an error, we can choose from any number of built-in Python exception types. Here's Python standard documentation on built-in exceptions, and at the bottom of the page, we have a list of all the built-in exceptions and the hierarchy in which they exist. Remember that exceptions are classes just like any other, so they can be placed into an inheritance hierarchy, and that's what's been done here. Some of them are familiar, and some you will never have seen before. Usually the ones that we'll choose will be in this range, the ones that inherit from exception. Some of the exceptions are actually under the warning type. These we see far less often. Now, of course, everything in Python is an object, which means that every object type is also a class. When we raise an exception, we're really constructing an exception instance, which will have attributes just like any other instance. And like we can create our own classes of objects and inherit from built-in objects, or the parent class of all object, we can create our own exception classes. We would do this in order to have our exception do more work than just display an error message. It could log the error, it could inspect an object. Really, it's up to us what it does, although usually a custom class won't do a great deal more than display a message. The type of error is itself significant, of course, and we often create our own error types so that we can indicate a particular situation that Python doesn't normally cover. For example, if we're having some kind of network outage where the database is acting up again in a way that we're familiar with, we might create our own exception types for that so that other developers encountering the error will know exactly what's going on. The myError exception class that we've created here shows two basic methods that are automatically called during the exception handling process, init and stir. Of course, you're familiar with init. It's the method that gets called when an instance is created. And the stir method will get called when the exception is raised. So usually they're called in close succession. What we're doing here with args is capturing any arguments that are passed to myError. And this is the standard behavior of most built-in exceptions. If you're not familiar with it, the star args that we put in the arguments list here will accept any number of arguments. It's a special pattern matching mode for functions and methods. It basically says that if you pass any arguments to the function or method, the objects will be stored in a tuple called args. But we can also pass no arguments. in which case args will be empty. And as you can see, we're raising myError both without any arguments at all and also with an argument. So what we're doing here is if there are any arguments being passed, we're going to decide that we're only interested in the first one. And we're going to take that first argument that's passed and store it in an attribute called message. If there is no argument passed, we'll store it in an attribute called message. MyError here is being raised without any parentheses. In other words, it doesn't look like a standard object construction. And that's just a syntax help that Python adds when raising an exception type. You can choose to include parentheses with an argument or arguments, or you can omit them altogether. So we're doing something very similar to what built-in exceptions do, and that is to take any arguments and store them in message. And actually, I think I will replace none here with an empty string because I think that's also a default behavior, not that we need to follow the defaults. Then when stir is called, and that's really what's happening when we invoke the raise statement, we have the object to play with. Just like any other method, the myError instance will be passed, and we can display the message attribute if we like. So inside of stir, we're showing that stir is being called, and then if there's a message, we'll return here's a myError exception with a message, and if not, we'll just say here's a myError exception. Let's try this out and see if there are any other errors. So the first time we ran it, it said calling init. We then have a trace back saying that we've raised myError, and we said here's a myError exception. And since that terminates, we should then go ahead and comment this one out, run it again, and see here's a myError exception with a message. Houston, we have a problem. So this class actually does what a lot of exception classes appear to do, that is to display a message if one is passed. But our choices are unlimited here. We can also create a hierarchy of exception classes that can take advantage of inherited functionality if we wish. So in this lesson, we got a brief peek at a custom exception class. Classes of this kind are not brought into the mix unless we're working in a larger scale class system where custom errors have special meaning within the context of our system's purpose. For example, we were doing a lot of networking, we might create some error classes that describe and handle types of networking errors. And you'll find that importing custom libraries can sometimes include a set of new exception types as well that relate to that library's purpose. By creating our own exception types, we can fine-tune the types of errors that we're able to raise, and thus communicate better with our user when things go wrong. In this assignment on exceptions, we'll build on the solution that we built in the previous assignment and add some exception trapping, as well as a custom exception class to handle potential errors. In case you haven't looked at the solution to the previous assignment, I'm about to display it. The overall assignment here will be to trap any errors that might occur due to mistakes that the user makes. At this point in our work, when we're building classes that others may use, or that might be used within a larger system, we want to consider how our library code can not only be used, but how it can be misused. It's important to be able to trap and handle user errors because they're the most common type of error. Now, we're going to be using exceptions to trap certain conditions in our own code, but in this assignment, we're going to think about what might happen with the user. And it's important to be able to handle the error when it occurs. So what I'd like to challenge you to do is to think about your config_dict class from a usability perspective and ask what you might do to handle any errors that could occur. I'd also like to see if you can create a custom error class that can handle the dict key error by listing out the keys from the config file that do exist. So what could go wrong? What if the file doesn't exist? So the user will begin by creating a config_dict object. What if some file.txt doesn't exist? Well, in our current solution, it's actually pretty simple. Down here, we'll just open it for writing, which will create a brand new file. But here's a question. What if the path is a bad path? Then this open for writing would fail. So we need to be able to trap this. But this introduces a small awkwardness because if we allow them to pass a bad path in the constructor, and then when they try to write to the dictionary, we're going to trap an error here, it's a little late to be telling them that it's a bad file name. So it sounds like we're going to need to put some code up here in the constructor that confirms that the file can be open and written to. And if it can't be, we're going to get a certain type of error, and part of your job is going to be able to figure out what type of exception results. And then you'll want to trap it and do something about it. The other possibility is that they might ask for a key that doesn't exist. Now, do you know what happens when you ask a dictionary for a bad key? You'll get something called a key error. And it's not a terrible error message because it's somewhat descriptive. What would be great, since we're working with a config file that supposedly has keys that the user wants to access, is if we have our program respond with an error message that actually lists out the keys that are available in the config file. That way the user won't have to actually dig into the file to see what keys are available. So I'd like you to create a new exception class called config key error that is constructed with two arguments. The config dict object, that would be self, since this error is being handled inside the class, and the key that was requested. So it looks like we're going to have a get item added to our class with the second argument, obviously, when they're accessing a key. And if it's a bad key, a key error exception will be raised. We should trap that and then raise a new exception. I'll indicate that there's some code in there, and then somewhere along the line, we'll raise a config key error with the object and the key that was asked for. And this would only be raised, obviously, if there was a bad key. So we'll be trapping a key error exception and then raising our own customized exception class instance. And as I said, the config key error should list out the keys that are available in the dict. And obviously, it'll be doing that by looking at self, which is being passed to this exception. If this doesn't make perfect sense the way I'm explaining it now, don't forget there's always a written version of the assignment in the working files. I've also placed in the working files a program for testing this class. Basically, you can call it three ways. Without any arguments, it'll read out the entire config dict. With a key and a value argument, it'll set that in the dict. And then also with just a single argument, it'll retrieve and return the value associated with that key. And this will give you ample opportunity both to set keys and values in your dictionary, to inspect them, and also to pass bad keys so that you can trap the error and see what happens. If we call the script with a key and a value, it'll write the data. If we call the script with a key that exists, we'll see the value. We wrote A to B, key A, value B. And when we ask for A, it reads the value and says the value for A is B. Finally, if we call it without an argument, we'll see a listing out of all the keys and values. And then if we make the mistake, we passed in a single key, meaning we wanted to see the value for that. We got an exception, and it was a config key error that was raised. And it says, key X not found, available keys A and C. So you can use this calling program, again, which is in the working files, and then a successful completion of the assignment will display the output in this demo. Okay, here's my solution to assignment 4. You may come up with a more optimal solution than mine. At this point, I think you want to be able to use your judgment and perhaps some of the qualities that I said good code will have to evaluate your own solution and comparing it to mine. So what's changed here? The first thing we did was we made sure that the file path was writable. If all the user passes to the constructor is a single file name, then it'll have no problem creating the file. But what if they pass a path and the path is invalid? Or it's even possible that we don't have permissions to write in the directory where we're executing the program. In either of those cases, we won't be able to open the file. And rather than check ahead of time to see if the file is writable, we just go ahead and do it and then trap the error if there's a problem. Here, by the way, we're opening the file for writing and then we're closing it right away. We only did this just to see that it could be done. If it can't be done, we'll get an I/O error, input-output. This means the operating system refused to comply and pass the error back to Python. Python raises an I/O error, and we trap it here. And then we re-raise it. It's still an I/O error. It probably should be shown as one. But what we did was we added a message. You made a mistake, and here's what you need to do to fix it. Now, you could have put exit here, and that would have been fine. I'm choosing to re-raise it because I still want it to be an exception. That's probably the best practice in this case, because we're writing a library for others to use, and we don't just want to summarily terminate their program if something goes wrong on our end. Rather, as we discussed, we probably want to bubble the error back up so that they can handle it if they wish. Or if they don't handle it, it will terminate the program. Then this part is mostly the same, and I believe setItem is the same too. GetItem is where we're going to get into our custom exception class. If the key can't be found in the dictionary, raise config key error. Now this is the custom exception that I was asking you to write. And passing self, which is of course our dictionary object, or it's really our config dict object, but it can be treated like a dictionary since we inherit from dict, and the key that was requested. Notice that right after raising this error, a line that says return the key and the value. Obviously, if we're raising the error, we're not going to get to this line. But if we don't raise the error, we will. So this is our if-then logic. If we can't find it, raise the error, and that means take off and go to the exception. But if this doesn't turn out to be true, that is, if the key can be found in the object, then we just get to this line and return the value. So now the config key error exception. As we explained in the video on custom exceptions, we have access to init and stir magic methods. When we raise an exception like this, we're actually constructing the instance and printing it at the same time. Init takes the object that we passed, which is understood to be a config dict object, and names it this up here in the method, and the key that was requested. We're storing it right here in the object because when the error gets raised, which it's about to get raised, we want to be able to pull it out of the same config key error object. This was actually the config dict object, and self, of course, is config key error object. So we set two attributes in the config key error object. Key, which will be the key that was requested, and keys, which will be the keys that are available in the config dict. Remember, our purpose here was to show what keys are available so that when the user requests a bad key, he or she will see which keys are available. So down here in stir, we have a message, key 0 not found, available keys 1. And we're using the string formatting method to pass the key that was requested. So key, whatever key was not found, and then available keys are taking the keys and joining them together on a comma. In this section, we'll discuss object serialization, which means different methods by which we can store objects on persistent storage, in other words, the disk. Sometimes serialization is also referred to as object persistence, and persistence, of course, means storing data between executions of a program. So you run a program, it writes something to disk, the program ends, next day or next year, we run the program again, and the data is waiting for us on disk. If what we've stored on disk is actually a Python object, then we can say that the object was made persistent. When we think of writing data persistently, we might normally think about databases, which are often organized into tables, or in math terms, relations, which is where the term relational database comes from. And that's a form of persistence, but it's not object persistence. This section is about object serialization or object persistence, which means we'll attempt to store our Python objects as objects. Pickle is probably operationally the simplest way to store Python objects. A little like pickling, it lets you take the whole object and store it in situ, meaning in place. In other words, we create a Python object, we change its values, and then we just store it on disk. Now, it's possible to instantiate a pickle object and use methods on it, but the module also provides convenience functions for dumping and loading. So here we are dumping an object. MyList equals some list values. We open up the file for writing, we grab a file handle from it, and then we use pickle.dump with the object and then the file handle. And of course, running this won't show us anything, but we can say that the object has been stored. So now I've commented out the code where we dumped the object into the file, and I've replaced it now with an opening of the same file for reading, and then passing that file handle to pickle.load, which should return the same object. Sure enough, we get the object back. Now this is a copy of the object from disk. It's obviously not the same object as MyList, but the point is we were able to serialize the object without really having to do anything. You want to compare this idea to storing these values in some other form, let's say a text file or a database. Unless we want to write the object like this onto the disk and then maybe evaluate it later or something like that, Normally what we would do is we'd break out these elements by looping through them and then write each one to a line in the file or to a row in the database. It'd be more complex than this, obviously, because we're just talking about a very simple structure, but that's the concept of storing data persistently if you're not going to serialize the object. The benefit is huge. Just dump the object, and then when we load it, we get it back. We don't have to think of transferring the data to some other format. The downside might be that it might be a bit slow, but it's surely an extremely convenient way to store things. And if you're not worried about a little additional slowness, possibly a little additional space on disk, then it's a great option. Another easy way to use pickle is to call the dump_s and load_s functions, which write to a string rather than to a file. So I imported pickle. I'm using dump_s with a list object to store it in a variable. And then I'm using load_s to get it back. So if I print var, I'll see the object returned. X is a string, but it's not the object itself. Let's actually see what's in X. Pickle objects are not human readable. This is a string, but it's this particular pickler's method of storing the list. And the reason they might not be storing the list directly in a form that we can read is that this would be more compact, even though it's more characters. Now let's look at storing multiple objects using pickle. They tell us in the documentation that if you instantiate a pickle instance, you can write multiple objects to it. But I prefer to just keep to the convenience methods dump and load, dump_s and load_s, and just pile my objects into a tuple. As you can see, I have an integer here, a string, and a dictionary, and then also a list. This list actually looks a lot like database results, a list of tuples. Then I just use the convenience method dump and create a tuple here that contains each of the objects. And let's just run it and see what we get. After we've dumped it, we went ahead and loaded it into a new object called tup. Tup has 4 elements because that's what we passed in when we dumped the object. And now we come to my favorite part, storing instances. We can take any instance that's been created and store it along with its attribute values, which means that we can run code that creates objects. The objects change over time while the code is running, and then we can just store the object exactly as it is. We're creating a myClass instance, and we're calling increment on it twice. As you can see, the constructor takes a value and sets it in an attribute called val, and then we're changing the value. We then take the object, cc, and store it in pickle by dumping it. The data file closes at that point. We then go ahead and load it and print and see what we get. So we printed unpickled cc. This is the instance. We printed the attribute value, val, which is 7. That's correct. So we were able to successfully store an instance and its state in a file, which means that we could run the program later on, open the file again and unpickle the object, and just use it as if we had never stopped executing. In fact, we can store objects of any type, including functions and modules, as well as class objects, that is, the classes themselves. Python doesn't actually store module or class code, and it doesn't store class variables either. And I'm going to demo this for you by commenting out the class definition, the whole creation of the instance, and leave just the opening of the data file and loading of the pickle object. Now this part's going to work as far as pickle's concerned. It's going to take the instance out and assign it to this variable. But watch what happens when we run it. Module object has no attribute myClass. The problem is occurring when we try to actually deal with the object, which is only referring to the class to which it belongs. In other words, in pickling the instance, we haven't pickled the class, and even pickling the class object itself is not going to help. Again, pickle can't store code. It also doesn't store class attribute values. So if you want to pickle an instance, or a function, or a module, the code for it actually needs to be available. All we need to do is make myClass available again. We can even comment out this part of the code, and it should work. As long as the class code is available, the unpickled object will function properly. One other thing to mention about pickle is that its implementation and the formats generated by pickle can vary between versions of Python. Later versions of pickle should be able to open older pickle files, but an older version shouldn't be able to open a newer pickle file. So if you ever have problems reading a pickle file, you might want to check the version of Python that was used to create it and compare it to the version that you're using to read it. So in this lesson, we learned about the pickle module, which is extremely convenient for serializing Python objects. We also learned that although unpickling can store classes, modules, or functions, it doesn't actually store these objects, but instead will store references to them, and that they must be available to the script that unpickles them. For complex data structures like lists of lists or instances of a class that have a number of attributes set, pickling is an extremely convenient method of storing and restoring these objects. In some cases, saving us having to flatten or pour the data into a tabular structure that would normally be necessary when trying to store data in a database table or other tabular structure. In this lesson, we'll look at the JSON data structure format, which can be used to store complex structures like lists of lists, dictionaries of dictionaries, etc. For these purposes, JSON is very similar to Pickle, with specific advantages and disadvantages in comparison. So here's some sampled JSON from one of my previous stints as a Python programmer. As you can see, this file looks like a conventional dictionary. In fact, it was used to store configuration values to be used with our database backup script. We could easily have used Pickle to store this information. We could also have gone with the relational database. But consider that Pickle would produce a file that a human could not read. So take a look at this format of JSON. We're going to find that JSON formatted files are very similar in the use of braces. In fact, we could edit this file if we wanted to. JSON is a very simple format. That's part of the reason it's so popular. And by the way, JSON stands for JavaScript Object Notation, and it was designed for JavaScript originally, but it's since become popular across languages for this very reason. So we can load this config file very simply. We open up a file for reading, obtaining a file handle, then we pass that to json.load, getting back an object. Print the object. Let's see what we get. Same object that we saw in the config file. It looks like a dictionary, and in fact, I believe it is a dictionary. Sure enough, it's of type dict. So although it's following the JSON format for storage, it comes out as a Python object. And writing JSON is similarly as simple, and it uses the same function name as we saw with Pickle. Here, we're loading the JSON file into conf as we did before, and then adding a key and value to conf. And then we're using dump to send it back to the file. Let's run that and see what happens. Okay, no output, but let's check the file. Okay, looks like it's changed. Before it was printed very nicely, although there's our new key and value. And in the same way we did with Pickle, we can also print to a string with dump_s and load with load_s. So as you can see here, we're taking a dictionary of lists, passing it to dump_s, coming back with an object, which we then print. This object X is a string. It's coming back from dump_s, so it's dumping to a string. But keep in mind, it's not Python, even though it looks like Python. It's just a string describing the structure. We then take the string and pass it to load_s, brings us back a structure, and then we can work with that structure. As you can see, we're looping through it and showing all the keys. Now, as we mentioned, one of the reasons JSON is so popular is in its human readability, which is why many languages besides JavaScript support it. And also, as I mentioned before, a common use of JSON is to hold configuration files. And because it's human readable, JSON files are also human editable. But there are some caveats to be aware of when you're editing a JSON file. Here's one really easy to make error. And it's so easy to make because a comma like this at the end of a list of pairs or a list of elements is perfectly legal in Python. And it's legal in Python because if we have lists like this and we want to edit them, it's often more convenient to have a comma after the last element because we can move elements around or add new elements without having to worry about that last comma. You can even see that the IDE flagged it. Let's go back to our test program where all we're going to try to do is load this JSON file. And if it loaded okay, we won't get an error and we'll see this print message. Let's try it. And we get an error message, expecting property name, line 9, column 1. Now, if you were able to go to line 9, it would take you here. But the main problem is that JSON saw the comma and said, oh, I know, another key in this dictionary will be coming. But it doesn't see one, and that's why it gives us the error. So if we remove the comma, everything's hunky-dory with JSON. Another problem, quotation marks. Again, it's easy to mistake this structure for a Python structure, but it just isn't one. It's a JSON structure, and single quotes do not wash with JSON. Now this error message is even less helpful. No JSON object could be decoded. It's a little annoying because this looks very much like a JSON object, but it's not considered valid if the quotes are there. However, JSON doesn't really give us a useful error message. We just have to know this. Single quotes are not allowed. Let's see what the editor says. There you go. JSON standard does not allow single quoted strings. So your IDE can help you, but your IDE may not always be available. And it's fixed once again. Again, this isn't Python, and you notice that the true value here isn't capitalized. And in Python, a true value wouldn't be the true value if it wasn't capitalized. However, if we try to apply this to JSON, again, we're going to have a problem. And we get that same unhelpful error message. It doesn't tell us where the problem could be. And if we have a very large file, it could be a real issue in trying to determine what the problem is. But here's the problem. True is not capital T in JSON. It's lowercase t. So let's run it again, and we load it OK. So these are some of the things that you should keep aware of when you're editing a JSON file directly. You might remember that when we ran this code the last time, read the JSON file, and then reopened the file for writing, redumping the same structure, we got less than readable output. And let's look at that again. Now backup config is written out in a single line, and that's because JSON prefers it that way. Remember, JSON really is a machine-readable format, even though it is also human-readable. We can bridge the gap with a couple of extra arguments to dump. Here we're giving it an indent value of 4, and we're listing a tuple of separators. The comma to separate elements in a list or pairs in a dictionary, and the colon to separate key and value in a dictionary. So let's run that and see what we get. Okay, great. We're back to our human readable format, and that was because we added these new special arguments. So in this lesson, we learned about JSON, and we saw that it bridges the gap between machine readable and human readable. And we would prefer to stick with readability than some kind of hyper-efficient scheme that wouldn't be human readable. In this lesson, we'll look at YAML, a markup language that's even more readable than JSON and is used to store structured data. Apparently, YAML used to stand for yet another markup language, but is now supposed to stand for YAML ain't markup language, one of a group of recursive acronyms, including GNU, which stands for GNU is not Unix. One particular reason YAML might deny being a markup language is that it uses whitespace to separate its elements, thus eschewing the braces and brackets that we associate with other markup languages. Python's YAML parsing module is called PyYAML, and it does not come installed with Python. Installing is usually a snap as long as you have permissions to install. On Unix and Linux, the command is sudo pip install PyYAML. You just enter that in the command line. Of course, you're going to need sudo access, which means that you have permissions to write to default install directories. And on Windows, your installation is going to depend on the distribution that you're using. Some of them come with PIP, and you can just use that. Others would require that you install in a different way. Unfortunately, I won't be able to go into all the different methods that you would use, but installing shouldn't be too difficult as long as you read your documentation. Once you've installed PyYAML, you can load and dump multidimensional structures in a way similar to the way we did with JSON and Pickle. We'll start by importing YAML and creating 3 structures, a dictionary, a list, and a tuple. And then for each one of these structures, dumping using YAML, so YAML.dump, the structure, and it's assigning to a new variable, which we're printing. And then here we're just printing the outcome of the other 2 calls, which are identical. We're just dumping each of these structures. And what we get as a result is the dictionary, the list, and the tuple. And you can see what the notation looks like for each one. The dictionary is notated just about as simply as it can be. Key colon value, key colon value, key colon value. White space will separate the different objects in some cases. And you can see a list is notated with dash element dash element dash element. And then finally, a tuple, which has to be identified as such before it uses the same notation as a list. So let's dump a more complex structure and see how YAML handles it. We're starting with a tuple, and this tuple contains several elements. The first one's a list. The next one is a dictionary. And then we have after that a list that contains a dictionary and then 2 integers. And then finally, another dictionary. Let's just see what we get with this arbitrarily complex data structure. Well, it looks like we start with the Python tuple. This is the first element, and in that element we have a list. Then in the second element we have a dictionary. And then in the third element we have another list. So you can see how simply notated it is, and yet it's quite precise about what it's showing. The indents are indicating nesting. The dashes normally indicate a list, unless we have the notation Python tuple, in which case the dashes mean tuple elements. And then finally, another dictionary at the end of that tuple. Now let's look at loading a YAML file. For this, I'll use a real-world example, a YAML file that's intended for Google's App Engine. I've talked about Google App Engine before. Basically, it's a web framework, and it allows you to write programs that will be served out on Google's infrastructure. In order to set one up, you need to set up a configuration file, and this is a sample one with some of the values changed. And it looks like we have a 6-element list associated with this key. So I'm seeing a dictionary that includes a key associated with a list. And then what's inside this element of the list? Key colon value, another dictionary. So I think what we're looking at is a dictionary of lists of dictionaries. Now we're going to use the load function to take a YAML file, that's app.yaml, the one we just looked at, parse it, and turn it into a data structure that we can use in our Python program. We're saying with open file as file handle, load file handle. Now previously we did a dump of structure to a string. And you may remember that with Pickle and with JSON, we had functions called dump and load, and then also dump_s and load_s. Dump_s and load_s would work from a string or go to a string, whereas dump and load just worked with a file handle or other file-like object. But YAML is a little more convenient. If you pass it a string, it'll work with a string. And if you pass it a file handle, it'll work with the file handle. So we don't have to remember to use dump_s or load_s. Just pass a file handle or a string, and YAML will process it. Let's take that structure that we just looked at and see what it looks like after we've loaded it. Okay, that's not very readable. Why don't we use JSON's pretty printing to see the structure more clearly? I'll just import JSON, and then having pulled out the structure, I will say JSON dump_s struct, and then I'll give it some indenting specs so that it can do something pretty for us. Okay, that looks correct. Let's try that. Okay, so let's see if I was right about that structure. It's a dictionary with keys and values, and then one of the keys is associated with a list, and the list contains dictionaries. Let's look at, again, the YAML file and see what that looks like. Again, key-value pairs, then one key associated with a list, and each list has a dictionary in it. All of the string values, which need to be quoted in a Python structure, don't need to be quoted in YAML. So we're totally getting rid of all of the braces and brackets and all of the quotation marks that seem so necessary in other languages, but apparently aren't really necessary as long as we're keeping it pretty simple. Now, the last thing we'll look at is how YAML handles things like classes and instances. And you may remember when we talked about Pickle and JSON, those libraries can serialize instances. They can also serialize classes and functions. The code is not actually stored. So any instance that we store will retain its state, that is, its attribute values are retained. But in order to use an instance that comes out of Pickle or JSON, the class from which it came needs to be available. Otherwise, when we refer to it, Python won't be able to find the code that's necessary for using it. And in YAML, this is also the case. We have a class that has a class variable, has an init and an increment, and when we create a new myClass instance, it gets a value set in its attribute, and then when we call increment, that value is incremented. if we pass 5 to my class and get back an instance with an attribute of 5 and increment it twice, we should see 7. So now that we've created this instance and assigned it to the variable x, we can take x and pass it to dump, storing it in a YAML file. Then, just for demonstration purposes, we're going to pull it straight back out of the same file and assign it to a variable called inst, and then print inst val to see what happens. And we do get 7. So you can see that the instance was stored in the YAML file. But just to repeat a demo that we saw before, if we comment out the class so that it's no longer available, and we'll just say, okay, open up the file, pull out the instance, and let's look at its attribute, we'll get an error. And the reason we can't see what we want to see is that the instance depends on the class being available. And thus, when we store instances, we're really just storing the state of the instances. We can certainly serialize them and bring them back, but we have to make sure that the class is available. All three of these technologies, YAML, Pickle, and JSON, will store instances for us, and the state of the instances can be stored as well. But because an instance can hold just about anything, you need to be careful about the source of any object that you pull out of memory and deserialize. So if you should get a YAML, Pickle, or JSON serialized object off the web, unpickle it, bring it back into code, and then start using it, it could contain malicious code. You need to be aware of their source. Now, usually we just pickle for our own purposes. But there is a method in YAML called safe-load, and it'll limit the loading of objects to plain Python structures like dictionaries, lists, and tuples, and not instances that belong to our class. Even if you can trust the class, it might even be a built-in library, an instance can easily contain malicious code. So in this lesson, we looked at YAML. It's a markup language that's used to serialize objects. And its advantage over JSON or Pickle is that it's extremely readable. So it's very suitable for setting up config files by people who are maybe not used to other types of syntaxes. On to assignment 5. We're about to build on the previous assignment. Here's the solution to assignment 4. For this assignment, let's take our configuration class from our last assignment solution and alter it so that it writes to a Pickle object instead of a text file. As you know, this class is designed to turn a configuration file, which is a text file holding keys and values, into a dictionary so that it's very easy to use. Our class inherits from dict, which makes it act like a dictionary. But we've overridden certain functionality in order to make it behave the way we'd like it to. Instead of writing to a plain text file, we'll write to a Pickle file, and we'll be replacing the reading and writing of the file with the appropriate function calls from Pickle. Instead of passing a file name to the constructor, I would like us to pass an identifying name. This would assume that all of our configuration files are located in one directory. We would no longer have to check to see if the path was correct. Instead, we'll hard code a configuration directory inside the class itself. This is what it is for me. All my configuration files will appear in this configs directory. Then, instead of passing a file name, I'll just pass a config name, and that would be the name of a Pickle file inside the configs directory. This is a minor enhancement, so you don't have to do it, but the idea is we can enhance the feeling of a built-in configuration system by just using a name to choose the config that we need. When a person creates a config, they can just say, give me the database programs config. They'd put in the word database or something like that, and it would look for a file called database.pickle. So what do we need to change in this solution? Because you can make a copy of this, call it assignment 5, and then just change the places where we're writing to or reading from a text file and substitute the Pickle file. For example, here we're opening up these files and then we're reading from the file line by line, splitting on the equal sign and establishing a key and a value. This is going to be much simplified since all we really need to do is unpickle the Pickle file that was there. If the Pickle file doesn't exist and we just create it and close, Pickle will fail if you try to read an empty file. So you may need to write an empty dictionary to the file so that when you begin reading from it, even if there are no keys and values, Pickle won't fail when it tries to read. It might be simpler even just to take the object now that it's been created and just dump it to the file if the file doesn't exist. That should have the same effect of creating an empty dictionary. Obviously, this would be replaced with Pickle load, Get item should stay the same, and set item, again, would not open the file and write to it with keys and values separated with equal sign, but instead you would just use pickle dump to store the object in the file. And this kind of enhancement is pretty cool because although we're changing something fundamental about the inner workings of the configuration class, we haven't changed the interface at all. Instead of writing to a plain text file, it's now writing to a pickle file. But obviously the operation of the dictionary is not going to change, and neither is the init. We did add this enhancement of creating a config dict, but that was just for fun. The main point is that the underlying implementation of this class has changed. The interface has stayed the same. And this goes back to one of the chief advantages of object-oriented programming. Once we've established an interface, if we can maintain that interface, other code using these objects will not have to change. And again, this is part of the benefit of encapsulation, the first pillar of object-oriented programming. Here's my solution to assignment 5. This is just my solution. As we talked about in the assignment, the only real changes we need to make are in the reading and writing of the config file. We also added the config_dir attribute to the class so that when a user passes a name to the constructor, the method will look for the config file in the config_dir, which is why we're saying ospath join config_dir and pickle name.pickle. So we're looking for a pickle file with the name submitted by the user inside the config_dir. And if the file doesn't exist, we go in and dump a bare dictionary. That's just so something's there for when we open it. When we get to this point, we know we have a valid pickle file, and we can open the file and load it into a dictionary. Now, since it comes to us as a dictionary, we're using the update method to take the dictionary that came out of pickle load, i.e. from the file, and update the dictionary, which is really an empty dictionary, here in self. You may have tried to call init here perhaps, or tried to construct a new object and possibly run it into a recursive problem there. But this is the solution I came up with. Just update the brand new object with the object that was dumped from the pickle file. Then get item stays the same, and set item, again, instead of writing to a file, it's dumping to a pickle file. Now, the huge advantage here is that in the class, we don't need to deal with the syntax of the configuration file. We don't have to think about the equal sign and splitting on it and making sure that it's the only split that we do. Instead, we can just use pickle load and pickle dump to serialize our object to file. In this section, we're going to look at some tools which can help us to test, debug, and examine our code. Of course, the larger part of our time spent programming is spent going over code that we've written, debugging, and optimizing it. So we'll want some tools in our toolkit for doing this. In this lesson, we'll look at the Python debugger, or PDB module, which is a powerful tool for figuring out what went wrong. My favorite debugging tool is just simple print statements. I let the program run and I print out values of variables that I'm unsure about. However, there are times when I like the program to pause execution and give me the chance to run some code, inspect the variables in play at the moment, step through a few statements in the code to watch things happen, and let the code continue to run if desired. Being able to stop the program while it's running can be a really powerful help. Many IDEs feature debuggers, and many of them are visual, which means they'll step through your code visually, highlighting each line as it's executed, and allowing you to place breakpoints in your code to pause execution and allow you to examine variables. An IDE debugger may be the perfect tool for you, or you may find PDB more compelling. PDB works alongside other wonderful command line tools like IPython and the like, so that's part of its advantage over an IDE. But as with all tools, the right choice will depend on your preferences. Let's start with a simple program that needs to be debugged, the set trace statement and the continue command. Begin by running this program and seeing what we get. Okay, 10. Now what this program is intended to do is sum up all the values from 1 to 10. So we should see the value 55 here, but we're only seeing 10. The error here is pretty common among beginner programmers, so maybe you see it right away. Now, in order to debug, I'm going to make a decision about where I want the program to pause because I kind of want to figure out what's going on. We didn't even get an error. All we got was bad output. So we have to figure out exactly what's going on here. The classic thing to do is to stop execution in a place where you think the problem might start to be happening. Basically, I'm stopping it after the first iteration of the loop. As you know, this loop is going to execute 10 times, one for every element and value. What I'm doing is stopping it after the first execution of the block before it goes on to the second, just to see how things look. Let's try it. Okay, now we've entered the PDB prompt, which means that PDB is taking control. And what it's displaying right now is the line that it's about to execute. So you can see that we're at the bottom of the loop. So the next line that it's going to execute is back at the top for val and values. Now we have the opportunity to look at variables. And I'm going to want to look at val to see that it's 1, and that's correct. We're in the first iteration of the loop, so val should be the first element. And then my sum, let's see what that is. Okay, my sum is 1, 2. That's correct too. We're simply going to add 1, and then the next iteration we'll add 2 to 1, hopefully getting 3. And then in the third iteration we'll add 3 to 3 and hopefully get 6. The next command that we're going to use is continue. You can type out continue or you can use its abbreviation C. Now we get the same output. PDB allowed execution to continue, and it took control again when we got back to the set trace. Now it's showing us the same thing because it's about to go back up and re-execute val and values. So let's look again. The value of val is 2, and the value of my sum is 2. Okay, that doesn't make sense. It should be 3 by this point. So we might ask why it's 2, and at that point we might discover the error. Let's try again just for fun. We'll continue, come back to the same place in the code, the third iteration of the loop. The value of val is 3, correct, and the value of my sum is 3. Now I'm seeing a pattern. My sum is always the same value as val. So now we look more carefully at our code and we see that my sum is 0, and it gets reset to 0 at every iteration of the loop. Of course, what we meant to do was set my sum to 0 before the loop begins, so that by the end, it can get the aggregate sum of all the values that we've added to it. And now I'm just curious, take set trace away. I just want to see what the IDE told us about it. Redeclared my sum defined above without usage. I'm not quite sure what that means, but let's find out because I'm curious about an IDE. This inspection detects unconditional redeclarations of names without being used in between, like this, def x pass x equals 2. It applies to function and class declarations and top-level assignments. Okay, I'm not going to go into that too deeply. I thought maybe it was going to warn me about this very problem. But the problem that we want to fix is really to redefine my sum at the top. Quit will take me out of the debugger, and then I'll just run the program again now without any PDB interference. Then I get 55. Okay, here's a slightly enhanced example. We're going to show you a couple of additional commands available in PDB that can be really useful. What I've done is I've taken the summing of the current value with the sum, and I've put it into a call to double val. Let's run this code and see that again we're getting that bad value. What I'd like to do right now is try stopping the program early and step through the code statement by statement. Once again, PDB has taken control after loading the double val function, and before anything else happens, we're stopping. You can see why we're seeing values equals. That's the next statement that's about to be executed. Rather than continuing, let's step through it line by line. I'll type n, and you can see I get to the next line. So at this point, just to be clear, values has a value because it just got assigned. My sum doesn't yet have a value because we're just about to execute this line. We haven't executed it yet. So let's execute it. I'll say next again, and we've entered the loop. Now we're at my sum equals double val, and now for val and values. So as you can see, the next command did not enter double val. The reason is because the next command will take us to the next statement within the current context, or frame as they sometimes call it. The current frame is this area of execution. When we run a function, we're entering a new frame. We call double val, and then execution passes up to this function, and then executes the lines in this function. Once this function's complete, we return to where we made the call, and that's back to the original frame. And you may recall that I called it a stack as well when we were talking about stack traces. So we can check my sum and see that it's 1. That looks good. Let's keep nexting. Come back to the end of that loop again and check the value of my sum. Oh, it's 2. That's worrisome. We'll do another next, another next. Now we're once again at the end of the loop and before the beginning of the next iteration of the loop. We check MySum and we see 3. Now we really know something's wrong. Next, next, MySum and it's 4. Okay, obviously something wrong with the double val function. So how do we get in there? Well, we can use the other command that lets us go through statement by statement, including passing to other contexts or other frames, and it's called step. We use S for that. So now we're about to call double val. We do call double val. You can see now we're at the start of the function, and now we're inside the function. At this point, we can check things like argsum, which is 4, and val, which is 5. Obviously, that's supposed to be 9. We'll step again. Now we're at new val equals argsum plus val, and we'll check new val because that's what's being returned. 5, that's incorrect, and maybe at this point we'd be able to identify the problem, which is that we're resetting argsum to 0 at the beginning of every call to this function. So the essential difference between next and step is that next will keep you in the current context and will not enter any functions that are called, and step will. So then you may ask, why don't I just stick to step and not use next, since most of the time I'm wanting to visit functions that are called? Consider that we're often using libraries that we didn't write. Many times we're making calls to functions that concern code that we have no control over and that are probably not related to the bug. In those cases, we definitely don't want to enter those functions. Many of them are extremely detailed and make other calls to other functions within the library or other libraries that these modules have themselves called. So step is useful when you want to enter a function, but many times you really don't. And so in those cases, you would use next. List shows you the code and your position within it. Now, the way we're running it here, we can see our code, but a lot of times the code is so long that it's hard to get it all into one window, and you might be jumping around into different functions. So list will show us where we are in the code. Again, this would be the line that's about to be executed. And the last is help. If we type H, we can see a list of commands that are available. Now, we haven't had a chance to go through all of the commands that are available with the Python debugger, but in this lesson, we learned about it, how great a tool it is, and how it can really come in handy, although it isn't the only tool available for this purpose. You may want to check out a visual debugger that's available in an IDE, like PyCharm, just to see which one might be preferable to you. But we do know that the Python debugger will always be available in any distribution of Python, and that it's really useful on its own. This lesson is about logging and about Python's logging module. Logging is just print statements emitted by our program while it's executing. And there's a few different reasons we would want to log. In the beginning, we might just want to log messages for everything that happens because we want to use it to debug our program. Later on, we might only be interested in things like warnings. Because the program's running fine, we just want to know if something goes wrong. So what we do is we insert statements into our program and we set a severity level to each statement. We might have dozens and dozens of debug statements in our program and only a few warnings. Then, when we're running our program, we get to choose which log messages we'll see. So if we're not interested in debug messages anymore, they stay in our program, we just turn them off while we're executing. Here's a basic example where we're logging messages with a severity level of info or above. You can see we've imported logging, and then we say logging basic config, and we set the level here. The level is logging.info. And as we saw on the slide, there are several built-in severity levels that we can place here. Then our program has 3 statements, a debug statement, info statement, and a warning statement. Because the debug statement is beneath the threshold of info, it doesn't get printed. All we would need to do is change it to debug to see that message too. Of course, now this print statement is no longer valid. The default, if we don't set a level at all, is warning. So again, the basic usage is to log every type of message and leave those statements in our program permanently. Then later, when we decide that we don't want to see most of them, we just change the severity level. The logging levels that are built in actually resolve to integers. See, debug is a 10, info is a 20, and warning is 30. They're separated by 10, I think, because you could set your own custom levels in between those if you wish. And it is possible to use that level in your logging although we're not going to go into that part specifically. We're just going to focus on built-in behavior for now. So back to setting the level with the basic config function. You can also log to a file quite easily by just using a file name argument. Now, instead of logging to the screen, all logging messages will go to a file. This is usually preferable. The most common approach is to log everything to a file so it can be reviewed later. But if you want to see the messages as they come in, you can use a tail on a log in Unix to see the file updating in real time. You can also choose to wipe the log before every program run. The default is to append to the log, and that's usually what we want as well, because we'd like to be able to go back if we want to. Even if the messages aren't interesting to us for a particular run, we can just add them to the file and they won't cause any problems. So this would be an unusual usage, although it might be something that's just clearer and easier for you. We can also include a date stamp with our log. Here I've added the ASC time, that's ASCII time, along with the level name and the message to indicate what I want to see in the error message. And now you can see it's a very precise date and time, including milliseconds. And if we wish, we can format the date time to our own specs, if we're not interested in milliseconds, for example. Here I've placed the date, the hour, minute, and second, and the AM/PM value in the message. The formatting here follows the date-time formatting that you can find in the strftime function of the datetime module. So in this lesson, we took a very brief tour of the logging module for Python. This module is far more configurable and flexible than we're describing here, but the tutorial that you can find in the Python documentation from which I adapted this lesson is pretty clear and detailed. In this lesson, we'll talk about benchmarking, which means timing a section of code to see how long it runs, and then comparing its execution time with another section of code in an effort to optimize our scripts and help them run faster and more efficiently. Connected to execution time is memory allocation, and although they are certainly not the same thing, sometimes when a script is running too long, it could also mean that it's allocating too much memory, or using memory inefficiently. Now, monitoring your memory usage is a different task, and it can be important if you're working with enormous data sets and possibly overtaxing your computer's memory. But for many Python applications, memory is just not an issue. In fact, time of execution is also a non-issue in many applications of this language. We might even go so far as to say that if your script needs to be fast or memory efficient, you might want to consider using a different language. That's not to say that there aren't prominent Python developers who think about and discuss the efficiency and speed of their programs. But as I say, in many domains that have made the decision to use Python, memory and time are not usually important concerns. There are two ways to call timeit. Let's use a script first and test to see what can retrieve a value from a dictionary more quickly, by using a subscript or by using get. As you can see, we're saying timeit.timeit with our statement. The first statement is mydict C, so we're getting the value associated with the key C. And the other one, mydict get C, the same operation. Although, as you may know, get doesn't raise an exception if the key doesn't exist. And in fact, you can propose a default value for it to return if it does. Now, of course, Python's going to ask us what we mean by mydict unless we actually establish mydict. So we have a setup argument, and we've established the same dictionary in each of these. Then the number. We're going to execute the code snippet 1,000,000 times. Not the setup, but the statement. That's because these things happen so amazingly quickly. We need to run it many times to really get an idea of how long it would take. So let's execute this one. Index access is far faster than dict.get. We can run this multiple times to see how it varies. The execution time is going to vary in part based on what exactly is going on with the rest of your system at this time. So one of the techniques that we should follow is to run the test multiple times to get a better idea of what the real value is. And now let's do the same test from the command line. You don't actually have to create a Python script to do tests like this. We're calling Python, and the -m indicates a module import. So we're importing timeit with this part of the statement. Then the n obviously is the number of times the snippet is going to be run, and then the setup statement. Finally, the last argument is the snippet that we want to run. This one doesn't take a flag because it's just the basic argument. Please test this statement. We ran this and we got the best score of 3. And let's run access through the index far faster than .get. So I know which one I'll be using more often. By the way, we can test multiple statements and multiple lines of code by using a triple quoted string in the program version. And here's how we might call time it if we wanted to test a call to a function. We might put multiple statements in this function and just see if it works better than, let's say, another version of the function. So the first argument to time it, the statement we want to test, which is a call to test me. But we do need to set this up properly. We can import the function by saying from main import test me, because clearly this test runs in its own namespace. So we can't assume that it's going to be able to see this function even though it's right here in the main namespace. So we say from main import test me, and main of course being the current namespace. Then we're setting up the dictionary and setting up the value of key so that we can then call mydict and key. Finally, a short note on test results. Firstly, we notice that we get different execution times for multiple runs of the very same test. So it's important that you run tests numerous times, as I mentioned. Here's what's different from what you might expect. Let's say you run a test 10 times, and you want to figure out what's the most accurate time. It's suggested that you not take an average or a mean of these times. The variations in execution time have to do with what's currently running on your machine in the moment that you execute it. So it's suggested that you take the lowest time from all the executions that you run. This is considered to be the most accurate. Testing is something of an art, because the results of a test may not actually apply to your situation unless you can replicate the conditions under which the code is normally run. The tests that I ran in this example were against a 3-pair dictionary. The dictionary may behave very differently if it has 10,000 pairs as opposed to 3 pairs, and we're running an index access or a get access. I'm not saying you're going to see different results, but I'm saying that it's possible that you could. If, in this example, you expected that your script would be dealing with a much larger number of pairs, it might behoove you to try to create such a dataset for the test. You might also consider what other memory has been allocated at the time that this code is going to be run, because you're really just looking at this particular device in isolation. And when it runs in your code, the conditions may be different enough that you would get a different result. So in this lesson, we looked at the timeit module, and we saw different ways to execute code snippets and get a sense of which code is more efficient than which other code. This will aid you in writing code that runs faster and uses memory more efficiently. Memory and time are not often a concern for many Python programmers, but if you're working with large data sets or doing processor-intensive computations, then it will be a concern, and the timeit module can help. The most basic form of software testing tests the outcome of single functions or single method calls. Well-designed software usually consists of small units that are the functions and methods, and it benefits in testing because if we can test each small unit in isolation, we go a long way to verifying that that code is working properly. Each function or method is thought of as a testable unit, so we call this approach unit testing. And unit tests are an essential requirement of quality code. Some developers won't take a program seriously unless it comes with its own tests. Since code is so complex, we test the individual units in isolation, and then we have other types of tests like end-to-end testing that'll test the program as a whole. In this lesson, we're going to learn about PyTest, a testing module that allows us to write scripts that test other scripts. A Python testing script simply imports another script, calls each of its functions and methods, and then asserts various things about the outcome. PyTest does not come installed with Python. On Linux, Unix, and Mac, you can usually install with this command. You'll have to have sudo access, that is, root access, in order to install into standard directories. If you're working on a shared system and the system's being administered by another member of your team, you'll want to contact that person to have this module installed. Of course, the first thing to do is to simply import it and see if it already is installed. If it isn't, you'll need to install it or have someone do it for you. If you're on Windows, the pip command I showed you before may also work, but it depends entirely on which distribution you're working from. If you're on the active state distribution, for example, that distribution comes with its own module manager called ppm. I should probably also mention that there is a built-in testing package called unit test, which is similar to PyTest, but I feel that PyTest is worth the additional work of installing, so please install it for this lesson and for the upcoming assignment. Okay, let's look at a very simple program along with a very simple test. I'm showing you this all together, but this is meant to be two programs. First, we have a file called myprogram.py, which is the program that we're going to test. Here we have another program called testmyprogram.py, and this is the testing program. Now, my program has two parts. The first is the function that we want to test, and then it also has some executable code, which will be executed if we run my program. We're actually not going to run my program at all. All we're going to do is import it. When we import my program, we have access to its functions, so we can test its units individually. This gate, if you're not familiar with it, basically says that if we execute this script directly, we will execute these lines. But if we import the program from another script, all of the code will get loaded, but this part won't get executed. This gate ensures that any import of the code does not execute these lines. Because when we import a code, it loads everything, and if there are any executable lines, they'll get executed. We avoid this with this gate, and this is really the mark of any professionally produced software in Python. What we really want to talk about is testing the unit. So we begin by importing my program, and then we write a function called testDoublet. Now let's look at the names here. You'll notice that the test for my program is called testMyProgram, and the test for the doublet function is called testDoublet. This isn't an accident. In fact, the name test prepended to the name of our script and our function is required for Python to be able to find it. When we first run PyTest, it's going to look for any program whose name begins with test, and inside that program for any function whose name begins with test. Now we've chosen to say test my program and test doublet because it relates to the function that we want to test. That part's just for our benefit, but the test is required for this to be seen as a testing program by PyTest. Okay, so what are we testing? Well, doublet's purpose is to take a number, double it, and then return the doubled number. Our test of doublet is going to assert that if we call doublet with the value 10, we should get back the value 20. This is an assert statement, and it's core to what we do in unit testing. Let's look at assert in isolation. Assert is a simple statement. It's not required for testing. We oftentimes use it in our scripts as well. If we pass a true statement to assert, we get nothing back, and that's because assert is designed to be silent if everything's cool. If we're asserting something that's true, assert is good with it. But let's assert something that's not true. 6 is not equal to 10, so if we assert that it is, we get an assertion error. That means that we try to assert a false statement. The exception being raised is what PyTest looks for. If we're asserting this and it's not true, we're going to get an error. So let's go to my program as just the testing script. Again, we're asserting that if we pass 10 to doublet, we'll get back 20. The way we run these tests is by writing py.test. Doing that gives us a one-passed message. And the message means, hey, you had a test, I ran it, and everything was cool. The test succeeded. I guess we can verify that by making sure that a bad assertion would fail. Let's try this. This obviously is going to fail. Let's run it. Sure enough, a failure in the test. We could also test it by making the test correct and going in and making the function fail. Again, we'll get an error. PyTest shows us which line it was using to test and which part of the statement failed. And then it shows the assert statement with the values instead of the call. So it's asserting that 30 is equal to 20. So we get a failure. Obviously, if we restore it back to its former glory, we'll get a successful test. So this is the basic concept in unit testing. And when we write tests, we're going to be writing numerous tests. Most of our programs will be filled with numerous functions. And if it's well designed, the functions will be short, which means there'll be many more of them. This makes the program more conducive to unit testing since we have smaller units that we can test in isolation. Obviously, we're going to be testing functions to make sure that they do things correctly when we give them proper input. But another kind of test that we often do is to make sure that the function will fail properly if we give it bad input. Again, we're testing a unit in isolation, so we don't know what the rest of the program is going to do. We need to be prepared for the eventuality that it gets input that it wasn't expecting, and make sure that it fails properly when we do give it bad input. Looking back at doublet, We know what it's supposed to do when we give it good input, that is, an integer. But what if some other part of the program just erroneously passes a string to double it? What would happen then? Well, hopefully we'd get a type error, and we can test for that with another unit test. This unit test also tests double it, but it gives it a different situation to deal with. We're passing it a string. So hopefully we're going to get a type error. We test for that with the with statement. The with statement says, with PyTest raises type error. That means under the assumption that what we have in the block is going to raise a type error. It's sort of like saying, assert my program double it hello raises type error. We're just saying it slightly differently. We've written our second test to the function doublet, test doublet type, which, as you know, tests to see that if we pass an object that's not an integer or a float, it will raise a type error. Let's run it and see. Okay, error. Failed, did not raise. It did note that we got one pass, but we got one fail. It didn't raise the type error as we were expecting. I wonder why not. If we pass a string and we say string times 2, do you know what that does? It actually concatenates hello to hello in this case. It doubles the string for us. Obviously not what we want. In fact, we would like doublet to raise a type error if the wrong type goes in. So we're going to be okay with an integer or a float, and I think we can limit it to that. What we're doing here is testing to see if the type of the argument that gets passed is an int or a float. More importantly, we're saying if it's not an int or a float, raise a type error. Okay, excellent. It's doing exactly what we think it should be doing. There are even other kinds of numbers that maybe we'd like to be able to deal with. But since we actually do get non-erroneous result from using a string, it seems important that we be able to raise this type error if we're not passing the right type of value. So now let's run our test and see if it works. Interesting, we made an error. Guess that's because I should have used x instead of var. Okay, 2 passed. Terrific. So again, our test was making sure that if we passed a non-integer or float, we should get a type error. And now we've ensured that. In this case, you can see that the test actually helped write the function. And there's a whole approach to development called test-driven development, in which you write the test first, and then you write the code to fulfill the test. Because it ensures that we have a very thorough testing suite to go along with the code that we write. In fact, it ensures that we set up the conditions ahead of time for success by writing tests, followed by the code that's designed to fulfill that test. Once we've written a series of tests, and it's quite common to write dozens and dozens of tests for a given script, we can group together all the functions that test a particular script, along with variables that we may want to use, and we can write setup and teardown routines that are needed for a group of tests, which I'll show you in a moment. So now the same naming applies. We've started our class name with test because we want to identify it as a testing class, and PyTest will see it that way. We've also changed our test functions into methods by passing self to each one of them. Oftentimes our tests rely on data to operate on. The general paradigm with automated tests is that the test itself will provide the data. There are also entities called fixtures that will mock data for the tests to use. The idea is that tests don't normally operate on live data because they may make changes in the process. It's much cleaner and safer to have the tests operate on a temporary data set. For this purpose, and for any other process that prepares the environment for the test to run it, we can define a setup routine, and we can also define some cleanup jobs in a teardown routine. In our case, I'm going to use a rather silly example. In my program, I have a function called double lines. It's opening a file that's expected to contain integers, and it's calling doublet on every single integer in that file, and then writing the doubled list back out to file. So if the file contained 10, 20, 30, 40, 50, when we were done, the same file would now contain 20, 40, 80, etc. It would double values. And that's what this code is doing. It's reading from the file, creating a new list of double values, and then writing those values back out. We want to test it. And there's two things that's going to have to happen. We'll need to write a double lines test. And then secondly, we're going to need to be able to set things up so that we overwrite the file the way the function's supposed to do, and then at the end reset the file to the way it was before. I've created a file called testnums template, which contains some dummy data. Now, the idea is that we're going to overwrite this file with doubled values. Kind of a silly example, but it allows us to demonstrate setup and teardown routines. So test double lines basically does that. It passes a file name to double lines, and then it tests to see that the values are correct. Basically, the idea is that it's just going to contain the correct values from the beginning without having made any changes. Then when we make a duplicate, we'll put it in testnums.txt, and then we'll pass that to the double lines function. If we do that, we should see that testnums has been overwritten. And we should be able to see that the two files, the template file, which has the original values, and the testnums file, which now has the new values, should be related in that the new file will have values doubled. And that's what this test does. But what's important is that we have a setup method and a teardown method. The setup method copies the template file to the new testnums file, and the teardown removes the testnums file. In other words, the template is always going to have the original values, but testnums will be altered during the test, and at the end, we just remove it. So this is the idea of a setup method and a teardown method. And I'm calling it setup class and teardown class because it's basically doing the setup and teardown for all the tests in the class. So in this lesson, we looked at the PyTest module for testing our scripts. We saw ways to set up our tests, look at the assert and with PyTest raises tests, learned how to set up and tear down, and grouped our tests into classes. We learned that quality code must be accompanied with quality tests. This is really just a basic introduction to all the features of PyTest, but we're looking at some very useful and some common practices here. And we must write tests for our code. Although tests are really not much fun to write, they are an essential practice in the professional world. For our last assignment, let's write some tests on the program that we've been building through the last few assignments. Here's my solution to assignment 4. You can use my solution or you can use your own as long as it's working properly. Here is a list of the things that I'd like to verify that the script is doing correctly, including tests that ensure that the script is failing in the right way as well. If I create a new config.dict instance, can I say that it's of instance config.dict? It is actually possible to return a different type. Also, can I say that a config.dict instance is also a dict? Because since we inherit from it, the isInstance test should also be true. If I call a config instance and I pass it a file name, will it be stored in the file name attribute? What if I were to pass it a file name on a file that already exists? Can I be sure that that file will still exist after the object's been created? What about if I pass it a new file name? Will the new file exist after I construct a new instance? And what if I passed a bad file path to the constructor? In other words, what if I asked it to create a file at like my bad path? Will I get the right type of error? Most of these tests can be done by simply constructing a new instance of the object config.dict using a pre-established configuration file and then trying out its functionality. For example, the test for new instance is a config.dict, as well as a new instance is a dict, could be done in one test function that constructs an instance and then asserts that it's true. Why don't we just do that now? I'll create a new file in PyCharm, and I will call it test config.dict. Now, since my tests are going to go into a different file, I'm going to begin by importing the two things that I'd like to test. I'm going to create my own test class because it's good to group tests into a class. And if I want to test to see that a new object created through this class is of the right type, I can put it into a function. In fact, I'm going to check to see that a new config.dict instance is definitely a config.dict and that it's also a dict. Now this test basically creates a new config.dict. I put a temporary file name here. This would be like a config file name. Later on, I think we're going to be using a test file that we set up in a setup method. We're going to want to create some dummy data. So we're going to create a test config file that the instance can work with. For now, I'm just putting in a temporary name. We create a new instance and then we test the instance to make sure it's of the right type. Now, you might consider this a redundant test since it's pretty clear that the constructor for config.dict will return a config.dict instance. But generally, when I write tests, I usually like to just make sure that everything goes right and that everything is what I expect. So looking at the other tests, in the next test, the file name passed to init is stored in the file name attribute. we'd again create a new instance and then check the file name attribute to make sure it holds the value that we passed to the constructor. Now, there's going to be a little bit of figuring going on here, especially since you're going to be working with a temporary file, and you're going to need to be able to set up that file in the setup routine and then get rid of the file in the teardown routine. The way I solved it is something similar to what I did in the lesson. I used a template file. In the setup, I copied the template file over to a working file for the instance to use. Then I let the instance create a key and a value, and I read those. And then for the teardown, I just get rid of that file. The template file would continue to exist. The temporary working file would be created and then destroyed during the course of the tests. Here's my rather lengthy solution to assignment 6. I took assignment 4 and wrote a series of tests on it. And as you can see, there's quite a few tests for such a small module. There are really a lot of things that could go wrong, and not all of it is user error. For any given unit that we're testing, we want to ask what happens if bad input comes in, even if we're pretty sure that no part of the program ever calls that function. If you're working with other developers, you really can't control what they do, and they might end up using a function that you wrote incorrectly. You really ought to have a test that'll catch that, and importantly, be able to respond properly with the right error so that the situation can be resolved quickly. We begin by importing config.dict and config.keyError. I'm actually pretty sure we don't have to import this because we don't refer to it directly in this script. I imported OS because we're going to be working with a file and copying a file during setup. I imported PyTest because we need that for the with PyTest raises statement, and shutil, which is also about copying a file. I've grouped all of my tests into a single class. All of the tests become methods. And I've set up some file paths and test file paths to use in the setting up and tearing down. First, I want to go over some of the basic tests that we have here. The first one that I went over towards the end of the assignment is a new config.dict, a config.dict. And is it a dict? Then I want to know if I create a config.dict object with a particular file name, has the file name been added to the attribute? In other words, you can see that step by step, I'm checking to see that the class does the right thing. Now, what's test config.dict existing fn? It's a file name that I created. I've called it config.file.txt. Now, we could put this in a separate folder. As it is right now, we've got it in the same folder for convenience. But why am I calling it test config.dict existing fn? Why not just existing fn? A variable that's declared inside the class is a class variable and thus a class attribute. It's not a global name. So we can't refer to it as if it were a global name. We actually have to prepend it with the class name. So then all we're doing in this particular test is pass it a file name, which is config.file.txt, and then make sure it makes it into the attribute. Great. That unit is tested. Now, the reason I call this existing fn is because it's a file that's supposed to already exist when the test begins. There's another file that's called new fn, and I'm calling it config.file.new. For this test, I want to make sure that any new file name that's passed to the constructor results in the creation of a new file. So first I assert that the file doesn't exist already. That's just making sure that the test is ready to go. Then I create a new config.dict instance with the new file name. I check to see that that file name has been added to the attribute. And then finally, I check to see that that file exists. So we've tested two things here, to make sure that the file name gets added to the attribute, and also to make sure that the file is actually created. So I defined a bad file path, something that probably would never exist, and I pass it to config.dict. Now, what I'm supposed to get is an IO error, so that's what I'm expecting here. With PyTest raises IO error, send it a bad path and expect that IO error will result. If it doesn't, of course, then we're going to want to know about it. Next, I want to make sure that everything that's in the file is readable by the dictionary. And so I pass it the existing fn file name. And obviously this means that config file has some keys and values, and I know what they are. And then I come here and I ask and make sure that these three keys have been given the values of these three strings. I've even gone so far as to add an equal sign to one of the values to make sure that the split is working properly. That is, dividing the config into two pieces rather than three or more. And then I go ahead and check to see that a non-existent key will raise the config key error. Oh, and I see I am referring to it, so I did need to import it up here. Finally, I'm going to check for writing. If I write a key and a value to the dictionary, will it be reflected in the file? Now, the way that script works is, if you add a new key and a value, it opens the file, writes to it all the keys and values that are in the dictionary, and then closes the file. So I should be able to, right after having set the key and the value, be able to create a new config dict object with the same file name and find that key and value. As I said, writing tests can be a little bit tedious because you're basically just meticulously going over every line of code and saying, is that actually doing what it's supposed to be doing? Let's write a test for that. Let's write a test for that. And you'll end up with hundreds of tests. But it's great because at any point in the future, anyone can make some sort of change to your code. And if you want to make sure that everything's working the way it's supposed to be, just run the tests. If it's running through every single little test that every developer dreamed up, it's helping ensure that the code is going to be reliable. So unit tests are really great for establishing a stable state to the program and then ensuring it does so in the future as well. Congratulations on following through and making it to the end. Firstly, we learned the mechanics of building classes in Python. We discussed all the major facets of object-oriented programming, including the three major pillars: encapsulation, inheritance, and polymorphism. And we learned how to employ these techniques in our own classes, imbuing us with the power to build large, collaborative software projects. Digging a little deeper into Python itself, we learned how to take advantage of Python's core syntax, like operators, built-in functions, the with block, and attribute getting and setting, when used with our own object types. We learned how to inherit from Python's built-in data objects, like lists and dictionaries, and have our objects behave like them, but with specialized behavior. And we learned a little bit about Python's new style classes, which gives us a somewhat deeper understanding of how Python has evolved and its design approach. We learned about exceptions, how to handle them and raise them. Overall, we learned a tool set that can assist us not only in organizing our own code and handling its complexity, but more importantly, disseminating our code to others. Classes provide us with a method of designing interfaces, that is, code machines for others to use. In so doing, we've gained insight into how Python developers worldwide design their code and also gained insight into Python's design internals. Again, my purpose in bringing this material to you is to enhance your value as a programmer and to put your thinking in the direction of writing powerful, reliable code with a simple interface. The knowledge in this course is absolutely necessary for any programmer who wants to hold his or her own in the professional world. Understanding classes is essential for all aspects of the programmer's challenge, from writing efficient code to understanding the conversations going on online. Where do we go from here? Well, where would you like to go? I only ask because having a concrete idea of your purpose in learning this stuff will really aid you in determining your next steps. If you're interested in learning more about Python from an intellectual perspective, there's a number of valuable textbooks on Python's internals, going into depth on how the language is organized, and then reaching even deeper into the C implementation that determines how Python allocates memory, which can offer a deep insight on how to write fast and efficient Python code. Guido's History of Python is a fascinating read for those who wish to learn how and why Python's approach evolved from what was a rather different approach at the outset. And in the end, the Python official documentation itself can be incredibly enlightening and show you many things you would never otherwise have learned, if you have the patience to read through it. If you're interested in extending your skills at a practical level, there are also some textbooks which go into best coding practices and power tips. A recipes book can offer some amazing techniques for solving common problems, and in so doing can teach even more about Python itself. A book on writing Python according to Pythonic principles, that is, idiomatic Python, can give you insight into the best way to organize your programs and the most appropriate expressions of what you're trying to do. One quick note on online resources. Like any information to be found on the internet, advice on how to code is not 100% reliable. That said, I've found most website tutorials to be valuable and reasonably accurate, but you should always be on the lookout for a self-published expert who isn't always right about things. The best way to proceed is to consult multiple sources to get a consensus about something about which you might have some doubt. The question and answer website Stack Overflow is extremely reliable in my opinion because its answers are usually penned by experts and power users who take a personal interest in such things. And because crowdsourced voting on an answer, as well as other vigorous commentary to answers, helps ensure accuracy. And of course, the Python official documentation should be considered the last word on most matters technical. If your purpose is to get a job in Python, you're definitely in the right market as of the time of this recording. Python has never been more popular, and jobs in Python often command high salaries for experienced programmers, and that's likely to be the case for quite a while. Of course, it can be a challenge to get the kind of experience that you'll need for success in this field without having a job. My advice to students asking this question, how do I get a job, is to find work wherever you can get it. So you might look for opportunities in the job you have now. There are so many useful things a Python program can do, including summarizing or processing daily information, displaying such information on an internet website, etc. Or if you don't have a job or don't feel like there's an opportunity at your current job, you can look for opportunities to code on a freelance basis. There are numerous businesses that would like to feature their products online but don't really know how to begin. Of course, many of the more modest features are now commoditized by web hosts that have pre-canned applications, but there'll always be a market for a more customized application. If you can't get someone to pay you for the work, try to find a nonprofit or even a for-profit business that will let you do it for free. The point is to get projects and experience under your belt, something you can put on your resume, or something that you can visit on the web in an interview and say, I did this. What employers are looking for most of all is evidence that you can operate successfully in a professional setting and that you can do the work, but make sure that the outcome will help you in terms of experience and resume items. Lastly, there's always an opportunity to work within the Python community on open source projects that need programmers. It may take some ramping up to make meaningful contributions to most projects, but if you see that a Python open source project is being actively worked on and you're interested in it, you should contact the coordinators of the project, tell them about yourself, and ask how you might help. Open source programmers are among the most helpful and generous of tech professionals, principally because they're all working for the love of it. I have found the tech community to be largely helpful to me in all of my dealings with it, and I find it rewarding to extend that same spirit to my students and to others who I encounter in the field. As far as learning new technologies, there are always new hot libraries and frameworks cropping up, with varying levels of longevity. Rather than name specific technologies here, since the list will certainly be out of date at some point, I suggest you peruse job boards and try to talk to recruiters. There's a lot you can learn by being persistent. Good luck, and I look forward to hearing from you.